Greetings, and a very warm welcome to this sanctuary of nighttime discovery. This evening, our journey takes us out past the boundaries of what is known, venturing directly into those profound riddles that modern analysis has yet to crack. Despite the incredible breakthroughs and milestones we have achieved over generations, the cosmos remains intensely populated by deep riddles, bizarre contradictions, and serene secrets that no investigator can truly decrypt. Some of these anomalies are cosmic in proportion, sprawling endlessly across vast galactic networks and the crushing voids of black holes. Others reside much closer to our everyday lives, buried deep within our planet's oceans, floating through the complex currents of our sky, or hidden inside the inner workings of our own anatomy. These unresolved puzzles serve as a constant, humbling signpost that our systematic inquiry is not a static anthology of finalized data, but an unceasing, evolving chronicle whose chapters are actively being composed. Each hidden truth presents an open gateway into pure awe, reminding us all that we remain humble travelers exploring a reality that is vastly grander than anything our species can presently process. If you find solace and rest in letting your mind wander through these wonders of natural philosophy as you settle down for the night, please consider showing your support by liking this video and subscribing to the channel, or take a moment to write down your personal reflections in the comments section below. Your engagement is incredibly valuable as it guides other curious minds to find their way to this quiet space. For the time being, however, simply permit these grand questions to gently carry your consciousness away. Whenever you feel completely settled and ready, let us step forward into the dark. We are still completely in the dark regarding why the cosmos exists in the first place. On the surface, this feels like the most elementary, intuitive inquiry a human mind could possibly articulate. Why does an intricate web of physical reality exist at all, rather than a state of total, absolute blankness? Despite its simplicity, modern analysis possesses no definitive answer. The rules of physics are exceptionally skilled at mapping out exactly how our reality behaves once it has already been established. The field of cosmology can reconstruct the grand timeline of cosmic events all the way back to the monumental flash of the Big Bang. Yet, the fundamental reason for the universe being there to begin with, and the underlying cause behind the existence of precise natural laws that permit its structural reality, remains completely uncracked. When we look at subatomic physics, the mathematics implies that what we conventionally label as complete nothingness isn't actually vacant. Even a pristine, isolated vacuum in the freezing reaches of space is actually a boiling cauldron of subatomic movement, populated by phantom particles that instantly materialize out of empty space before tearing themselves apart and vanishing back into non-existence. A segment of the physics community proposes that the grand universe we inhabit might have emerged via this exact mechanism, operating under the principle that a state of total, pristine nothingness is fundamentally unstable, meaning that something is physically obligated to manifest from it. Meanwhile, an alternative group of thinkers asserts that our specific cosmos might merely represent one isolated bubble among an infinite sea of distinct worlds inside an incomprehensibly vast multiverse, where each unique domain bursts into existence governed by its own independent set of operational rules. However, even if we accept that radical premise as a factual reality, it merely dislodges our confusion and forces us to confront a far more profound dilemma. Why is the overarching multiverse itself present to begin with? Thinkers focused on metaphysics occasionally argue that physical presence is quite literally the default state of things, implying that a condition of true non-existence is a logical and physical impossibility. It could be that reality, in some incomprehensible manifestation, is fundamentally required to exist eternally. Regrettably, these structural paradigms are completely beyond our capacity to empirically validate. There is no observational telescope ever designed, nor any high-energy particle accelerator in existence that can isolate and quantify the exact reason why physical matter occupies reality instead of a clean slate. Every single branch of inquiry, every formula, and every discovery we celebrate relies entirely upon this singular, unverified, starting assumption. Every brilliant stellar furnace shining in the night sky, every individual subatomic component composing your muscle tissue, and every foundational rule of nature operates upon a mysterious bedrock that we are powerless to decipher. The simple, undeniable reality that our world is here at all continues to be the most deep-seated and impenetrable paradox our species will ever confront. Ever. The primordial catalyst that originally ignited our universe and set its complex machinery into motion remains completely shrouded in shadow. Through rigorous investigation, we can confidently trace the overarching chronicle of our universe backward across a staggering timeline of nearly 14 billion years, navigating back to an ancient epoch when all of space was compressed into a blisteringly hot, intensely dense cauldron of pure energy. We universally designate this monumental genesis as the Big Bang. But when we ask what specific trigger set off that initial burst, we hit a wall of absolute ignorance. Experts in cosmology have managed to assemble an incredibly precise microsecond by microsecond chronicle of reality, starting from the moment the universe was a mere microscopic fraction of its first second of existence. During that initial flash, an unimaginable burst of exponential growth known as cosmic inflation is believed to have literally ripped the fabric of space wide open. Yet what specific mechanism set off this inflationary burst? What caused it to instantly ignite, and by what means did it finally come to a halt? These foundational turning points remain completely unmapped. Certain theoretical models conceptualize the Big Bang as a spontaneous quantum fluctuation, a microscopic probabilistic shudder running through the very tapestry of existential reality that unexpectedly brought forth the metrics of space and time. Conversely, other frameworks propose that the Big Bang was never an isolated, singular beginning, but rather a temporary transition point within an infinite, unceasing loop of cosmic births, developments, and collapses, where individual universes expand outward, gradually slow down, implode back into a dense point, and instantly reset the cycle. Making this conceptual riddle even more difficult to wrap our minds around is the very nature of temporal reality. If the ultimate genesis of our universe simultaneously marked the literal birth of time itself, then trying to conceptualize what occurred chronologically prior to that event is a fundamentally flawed question that possesses no real meaning. Our most advanced scientific instruments, including the historic Hubble Space Telescope, the Planck Orbital Satellite, and the state-of-the-art James Webb Space Telescope, allow us to capture breathtaking, primitive images of our universe during its absolute infancy. Yet not a single one of these technological marvels can look directly into that absolute first instant of creation. We possess undeniable data that our universe had a clear beginning. We can accurately calculate its exact age, map out its physical expansion across eons, and capture the faint radiation left behind by its ancient fires. However, the primary ignition source that originally brought the cosmos to life, the true underlying initial catalyst, remains an ironclad secret hidden away in the deep dark of the past. Time proceeds forward with an absolute, unyielding consistency. Yet no scientist on Earth can explain the underlying physics of why this occurs. With every passing heartbeat, our immediate present continuously dissolves and transforms into the permanent past. We possess the cognitive capacity to hold vivid recollections of what occurred yesterday, yet we are entirely blind to the events of tomorrow. A shattered drinking glass resting on a hardwood floor will never spontaneously reassemble its shards and leap back upward onto a kitchen counter. Thermal energy naturally radiates outward from a hot mug of coffee into the cooler surrounding air of a room, but we never witness a cold beverage spontaneously absorbing ambient room temperature to bring itself back to a boil. Throughout our entire lived experience, the progression of time moves exclusively along a unidirectional pathway. Within the scientific community, this rigid, unidirectional movement is known as the arrow of time. What makes this reality so profoundly unsettling is the fact that the foundational mathematical laws of nature do not actually require this forward-only progression. When you analyze the universe at its most microscopic scales, individual subatomic particles interact, collide, and spin with identical mathematical precision, whether time is moving forward or being run completely in reverse. The foundational equations of quantum mechanics and relativity are completely symmetrical. There is absolutely nothing written into the bedrock math of physics that states time must exclusively march in a forward direction. Even so, the macroscopic reality we inhabit is entirely dependent upon this rigid one-way street. To make sense of this contradiction, researchers frequently tie the arrow of time directly to the principle of entropy, which dictates the universal law that closed systems naturally progress from states of order to states of chaotic disorder. The wider universe originally began its journey in a state of extraordinarily high organization and concentrated order, and it has been steadily unraveling, dissipating, and breaking down ever since, but this realization merely circles back to another deep mystery. Why did the cosmos begin its existence in such a highly specialized, ultra-low entropy state to begin with? Why was the dawn of space-time configured so perfectly that an arrow of time could even establish a recognizable direction? A segment of modern physicists hypothesizes that the perceived flow of time might actually be an emergent property born from the complex way information scatters across quantum systems. Others theorize that its forward march is fundamentally chained to the physical outward expansion of space itself. None of these theoretical frameworks, however, offer a truly complete or airtight explanation. The forward direction of time is a reality we exist inside of during every single microsecond of our conscious lives. Yet, the underlying mechanism of why it marches forward and only ever forward persists as one of the most haunting and unresolved paradoxes in the history of science. The overwhelming majority of our universe is constructed out of a mysterious substance that completely evades our sight. Whenever observational astronomers train their instruments on distant galaxies to measure the precise speed at which they rotate, they run into an inexplicable anomaly. The stellar systems located out on the extreme perimeter of these spinning galactic disks are traveling through space at a dangerously high velocity, moving as though they are being reined in by an immense, unseen gravitational anchor. Based on all established rules of celestial mechanics and the visible mass of the stars, those peripheral suns should easily rip free from the galaxy's pull and go flying off into the lonely cosmic void. Instead, they remain perfectly locked in place, maintaining their orbits. The logical deduction from this data is completely unavoidable. The vast majority of the physical mass occupying the universe is comprised of matter that is totally invisible to human eyes and sensors. Scientists have labeled this elusive mass dark matter. Dark matter does not illuminate the dark, nor does it reflect, absorb, or emit any form of electromagnetic radiation. Because of this, standard optical and radio telescopes are entirely incapable of identifying it directly. Even so, we can state with absolute certainty that it exists because its immense gravitational footprint directly sculpts the behavior of the visible universe around it. It acts as the invisible cosmic adhesive holding sprawling galaxies together, physically warps the trajectory of starlight, passing through massive galactic clusters, and leaves distinctive, subtle imprints across the grand geometry of the cosmic web. So, what exactly is this invisible substance? Experimental researchers have been hunting for clues for many decades. One school of thought suggests it is made of an undiscovered class of subatomic particles, colloquially referred to as WIMPs, or weakly interacting massive particles. An alternative hypothesis points toward axions, extremely light, ghost-like entities that barely interact with conventional atomic matter. There are even radical theories suggesting that dark matter might actually be composed of primeval black holes that materialize during the chaotic, high-density environment immediately following the Big Bang. Yet, despite dedicating immense intellectual and financial resources to the search, we still do not possess a single shred of definitive proof. Highly sophisticated detection arrays are currently buried deep inside subterranean caverns and abandoned mine shafts, waiting in absolute silence for a passing particle of dark matter to directly strike a single atom inside their pristine core. Thus far, these sensors have recorded nothing but silence. For the foreseeable future, this phantom mass, which is roughly 5 times more common throughout reality than the ordinary matter that makes up our bodies, our planet, and the stars, stands as one of the most monumental and challenging unsolved mysteries in physics. An unidentified, invisible force is actively ripping the very fabric of space apart at an ever-increasing rate. Back during the late 1990s, teams of astrophysicists who were systematically cataloguing distant dying stars known as Type 1a supernovae fully anticipated that their data would show the expansion of the universe gradually slowing down over time. Their logic was perfectly sound. The collective gravitational attraction of all the matter and galaxies in existence should logically be acting as a cosmic brake, slowly pulling everything back inward toward each other. Instead, the data revealed something that completely shocked the scientific community. The expansion of our universe is not slowing down at all, rather it is accelerating outward. This means that an entirely unknown form of energy is woven into the very vacuum of space, actively driving galaxies away from one another at compounding, terrifying velocities. We refer to this enigmatic phenomenon as dark energy, though we must recognize that this title is merely a conceptual placeholder that masks our profound lack of understanding. This mysterious dark energy accounts for nearly 70% of the total energy and mass budget of the entire cosmos. Despite its total dominance over reality, we have no real grasp of what it actually is. One prominent hypothesis states that it is an intrinsic property of a pure vacuum, a constant, unyielding baseline energy density that is naturally present throughout empty space. Another distinct possibility is that it signals the presence of entirely new physical laws, potentially manifesting as a fluid dynamic energy field that fluctuates in intensity over cosmic time. A few radical theoretical frameworks even suggest that this acceleration is a glaring warning sign that our foundational understanding of gravitational mechanics, pioneered by Isaac Newton and Albert Einstein, is fundamentally incomplete. What makes this cosmic enigma even more deeply troubling are the long-term stakes involved. The ultimate long-term fate of all reality is directly dependent upon how this invisible force behaves. If dark energy remains perfectly stable and constant for the rest of time, galaxies will continue to drift further and further apart over billions of years until the night sky becomes entirely black, leaving each local group isolated in a frozen, lonely void. If, however, this force steadily increases in strength, it could eventually culminate in a cataclysmic event where space expands so violently that it literally tears apart whole galaxies, rips planets from their stars, and shatters individual atoms. We can easily map its outward consequences with our instruments, yet its underlying nature remains a cipher. Dark energy remains the ghostly hand guiding the ultimate destiny of our cosmos. The fundamental parameters governing the physics of our universe appear to be meticulously balanced for the emergence of living organisms in a way that science cannot explain. The basic architecture of our cosmos seems to be perched precariously on a razor's edge. If the universal strength of gravity were even a tiny bit more intense than it is, stars would burn through their fuel and implode far too rapidly, preventing the stable development of planetary systems. Conversely, if gravity were just a fraction weaker, matter would never have coalesced to form galaxies or stars in the first place. If the electromagnetic force, which governs the interactions of charged particles, were altered by a mere microscopic percentage, atomic nuclei would be unable to hold on to electrons, and complex molecules would never bind together. Even the most minuscule, infinitesimal variance in any of these foundational physical constants would completely erase the possibility of life emerging anywhere in the cosmos. This deep scientific puzzle is universally known as the fine-tuning problem. Why do the foundational laws of nature happen to possess the exact numerical values that we observe? There is no obvious mathematical or structural requirement that dictates why forces like gravity, electromagnetism, or the strong and weak nuclear forces must exist at their specific observed strengths. Yet, if any of them deviated by even a hair's breadth, our universe would be a completely sterile, dead void. Certain researchers argue that this miraculous arrangement is nothing more than an extraordinary cosmic coincidence. Others suggest a more expansive view, that an infinite array of distinct universes exist within a grand multiverse, with each individual universe possessing its own randomly assigned physical laws. In this framework, we simply happen to occupy the vanishingly rare, hospitable universe that drew the winning ticket in a massive cosmic lottery, allowing life to arise and observe its surroundings. Another intriguing hypothesis is that there is an undiscovered, deeper unifying principle of physics that dictates these constants must take these exact values. For the time being, we have no way to definitively resolve the question. Yet, whenever we gaze up at the stars, observe our surrounding planet, and contemplate the reality that we are even here to ask these profound questions, we are left with the undeniable impression that our universe feels astonishingly, inexplicably tailored for our existence. Why this is the case remains one of the most stunning mysteries in all of science. No human being knows whether the wider universe extends outward infinitely without end, or if it terminates at a specific boundary. The portion of reality that we can actively observe, the observable universe, is incomprehensibly vast, spanning a diameter of roughly 90 billion light years. Even so, we are fundamentally incapable of peering past that perimeter. Because the universe has only existed for a set amount of time since the Big Bang, light travelling from the furthest reaches has only had about 13.8 billion years to make the journey to our eyes. This creates a hard observational horizon that we are physically blocked from looking beyond. But what actually lies on the other side of that cosmic boundary? One compelling hypothesis is that space is genuinely infinite, stretching out forever and ever in every imaginable direction, without any final wall or physical boundary. If this scenario is true, then the universe must contain an endless, infinite quantity of galaxies, star systems, and perhaps even an infinite number of planets identical to our own Earth. An alternative possibility is that the cosmos is finite in its total volume but possesses no physical edge, operating similarly to the two-dimensional surface of a three-dimensional sphere. In a universe structured this way, if you were to hop into a spacecraft and fly in a straight line for a long enough period, you would never hit a wall. Instead, you would eventually loop back to your exact point of origin. Astronomers are searching for clues to this riddle by studying the cosmic microwave background radiation, which is the ancient, faded heat signature left behind by the Big Bang. The minute temperature fluctuations and geometric patterns in this background radiation could reveal the true shape of space. So far, the data collected by our most advanced satellites indicates that the universe is remarkably flat. But this finding still doesn't tell us whether it is infinite or simply a massive, closed shape. For now, we remain completely ignorant as to whether the cosmos continues without end, or if it loops back upon itself in a grand cosmic circle. The true physical scale and geometric architecture of our universe stay tantalizingly out of reach, locked away just past our grasp. Far past the boundary of what our instruments can detect, there may exist a boundless realm of total unknowns. Whenever we peer out into the night sky with a telescope, we are simultaneously looking backward in time. The most remote galaxies currently visible to our sensors are hitting us with light waves that have been travelling through the void for over 13 billion years. But beyond the source of those ancient photons lies a massive domain that is permanently cut off from our sight. The unobservable universe. This grand cosmic horizon shouldn't be visualized as a literal brick wall floating in space. Rather, it is a structural limit imposed by the combination of the finite age of our cosmos and the absolute universal speed limit of light. Beyond this boundary, physical reality undoubtedly continues to exist, but we can never collect direct data on what is out there. It might be more of the same, endless stretches of galaxies, burning stars, and diverse planets rolling out far beyond our sight. or it could be radically different, with distant regions governed by entirely unique environmental conditions or even independent physical laws. Certain iterations of inflation theory, the model describing the explosive expansion space, underwent right after the Big Bang, suggest that our entire observable universe is merely one isolated bubble floating within an unimaginably larger, chaotic expanse of reality. If that concept holds true, the overwhelming majority of the physical universe lies completely outside the realm of human measurement. We are effectively trapped inside a small cosmic island, and the beautiful sky we can see is just a microscopic fraction of all that exists. The rest of the universe is out there in the dark, silent, unreachable, and cast in a permanent state of the unknown. A growing number of physicists believe that other separate universes exist, but we are currently powerless to prove it. The conceptual hypothesis of the multiverse stands as one of the most audacious and controversial propositions in modern scientific discourse. It posits that the universe we inhabit is not unique, but rather one individual member of a vast collection of independent worlds. Each separate universe within this framework could theoretically operate under entirely different laws of physics, experience completely unique historical timelines, and even manifest with different numbers of spatial dimensions. This startling concept emerges quite naturally from several of our most prominent theoretical equations. For example, the mechanics of cosmic inflation suggest that space could be continuously budding off distinct bubble universes, each containing its own specific set of physical constants. Similarly, the mathematics of string theory predicts a vast landscape of possible configurations for reality, with up to 10 to the power of 500 unique variations. Within these theoretical frameworks, our specific universe is just one individual roll of the dice among an infinity of options, which could elegantly explain the fine-tuning puzzle. We find ourselves in a universe perfectly suited for life, simply because life could never develop to observe its surroundings in any of the sterile universes. However, this hypothesis suffers from a massive roadblock. If these other universes exist entirely outside our observational horizon, we may never have a way to verify them. No light waves, gravitational signals, or information can ever cross the vast boundaries separating these realities. This makes the multiverse concept both deeply alluring and highly controversial. It pushes the boundaries of what can be considered science, because an idea that can never be empirically tested risks remaining nothing more than elegant mathematical speculation. Even so, the mind-bending possibility that reality is infinitely grander than our own universe remains one of the most fascinating enigmas in modern physics. The metrics of space and time might be woven from a set of deeper rules that our species has yet to discover. Albert Einstein's landmark theory of general relativity demonstrated that space and time are not a rigid, unmoving backdrop against which events take place, but are instead flexible, dynamic, and interconnected. They actively warp, bend, and stretch under the influence of mass, directing the orbital paths of planets and altering the trajectory of light. But when we look at the absolute deepest level of reality, what are the fundamental building blocks of this fabric? When we try to analyze the universe at its most microscopic scales, the smooth mathematics of relativity crashes directly into the chaotic rules of quantum mechanics. In Einstein's view, the fabric of space-time is completely smooth and continuous, but quantum mechanics dictates that when you zoom in close enough, everything in existence must be grainy, jittery, fluctuating wildly, and shrouded in uncertainty. Unifying these two wildly successful but conflicting theories into a single framework is the ultimate goal of modern physics. Several cutting-edge hypotheses suggest that space and time are not fundamental components of reality at all. Instead, they might be emergent properties born from something much deeper, such as an intricate network of quantum information or complex patterns of subatomic entanglement that generate the illusion of geometry. In this theoretical view, the space-time we experience is merely a surface phenomenon, and underneath it lies a deeper foundational reality that we cannot yet perceive. Other physicists openly wonder if time itself is an illusion cooked up by deeper static processes. If that turns out to be true, our most fundamental instincts about the nature of our lives and reality would be completely wrong. Space and time feel like the permanent stage upon which the entire history of the universe plays out. Yet the stage itself might be a deceptive illusion. What they truly are at their core remains one of the most profound, unanswered questions in science. A single subatomic particle can literally occupy two distinct locations simultaneously, and we have no physical explanation for how this occurs. The mathematical framework of quantum mechanics reveals that subatomic entities do not possess fixed, definite coordinates in space until they are directly measured by an external observer. Instead, prior to observation, they exist in a state known as superposition, a fluid cloud of mathematical probabilities where multiple contrasting outcomes exist at the exact same time. An individual electron can literally be here and there simultaneously, passing through two separate slits in an experimental barrier at the same time, and interacting with its own trajectory like a wave. It is only when an instrument or observer interacts with the particle that it collapses out of this probability cloud and chooses a single location. This isn't just wild, unverified theory. Experiments have repeatedly demonstrated superposition in action. Researchers have verified this phenomenon not just with microscopic electrons, but with complex molecules composed of thousands of atoms. Physicists can now carefully manipulate delicate lab environments to force macroscopic objects to exist in overlapping states of possibility. Yet, despite our ability to utilize this math, no one truly understands its real-world meaning. Does the particle physically split and inhabit two real places at once? Or is this superposition merely a mathematical reflection of our own ignorance regarding a hidden underlying reality? Certain interpretations of quantum mechanics suggest that reality splits into separate timelines every time a choice occurs. One world where the particle lands on the left, and another where it lands on the right. Others believe that objective reality is simply fundamentally fuzzy until a measurement takes place. Whatever the ultimate truth may be, the verified ability of a single particle to be in two places at once remains one of the strangest and most unsettling mysteries in science. Entangled particles can instantaneously mimic each other's behaviors across vast gulfs of light years, completely defying any logical explanation. When two subatomic particles enter an entangled state, their physical properties become deeply linked in a manner that completely ignores the distance separating them. If you measure a specific property of one particle, you instantly know the exact state of its entangled partner, regardless of whether it is sitting across the room or on the opposite side of the galaxy. Albert Einstein famously derided this phenomenon as spooky action at a distance because it appeared to completely violate his ironclad cosmic speed limit, which states that nothing can travel faster than the speed of light. Nothing should be able to transmit information instantaneously across space, yet every experiment we conduct proves that quantum entanglement is an undeniable fact of nature. Photons, electrons, and even small groups of macroscopic atoms have been successfully entangled and separated by vast distances. No physical signal or hidden message can be detected passing between them, yet their behaviors remain perfectly in sync. It is as if nature keeps an invisible master ledger that coordinates these particles instantly. What does this tell us about the universe? Some physicists suggest that reality is non-local, meaning that the cosmos is woven together far more deeply than it appears. When two independent subatomic elements become inextricably linked through the process of quantum entanglement, their fundamental physical characteristics become bound together in a way that completely ignores the physical distance separating them. If you execute a measurement to determine a specific property of one particle, you instantly discover the precise state of its distant counterpart, regardless of whether it is located in the very same room or positioned on the completely opposite side of the expanding universe. This instantaneous connection was famously criticized by Albert Einstein, who dismissively labeled it as spooky action at a distance because it directly seemed to challenge his ironclad universal speed limit, which states that no form of physical information or signal can ever travel faster than the speed of light. According to classical physics, it should be entirely impossible to coordinate information across space without any delay. Yet every empirical test we conduct confirms that quantum entanglement is an undeniable feature of our physical reality. Scientists have successfully entangled photons, electrons, and even small clusters of macroscopic atoms across vast distances, finding no physical signal or hidden message passing between them. Their behaviors remain perfectly synchronized, as if governed by an invisible master ledger. This deep paradox raises profound questions about the true structure of our universe, suggesting that the cosmos is non-local and interconnected in ways that completely bypass our everyday perceptions of space and time. Some physicists believe that this phenomenon might imply that space itself is an illusion, masking a deeper, unified quantum foundation where distance has no meaning. Others theorize that entanglement could be the fundamental mechanism that stitches the very fabric of space-time together, acting as microscopic wormholes that link distant regions of reality. Yet, despite our ability to harness this strange link for developing advanced quantum computing and ultra-secure encryption networks, the underlying mechanism that allows these particles to communicate across light years remains completely unexplained. For now, quantum entanglement stands as a striking testament to the counterintuitive nature of reality, showing that the universe maintains secret connections that science can observe but cannot fully fathom. A profound and deeply unsettling paradox arises when we attempt to track what happens to physical information when it falls into a black hole. According to the foundational rules of general relativity, a black hole is an object with such immense gravitational pull that nothing, not even light, can escape its boundary once it crosses the point of no return, known as the event horizon. This implies that whatever matter, energy, or structure enters a black hole is permanently sealed away from the rest of the universe. However, in the 1970s, the field of quantum physics introduced a massive complication to this picture by demonstrating that information can never be truly destroyed or erased from existence. In quantum mechanics, the past states of particles must always be reconstructible from their present configurations, meaning that the total amount of information in the cosmos must remain strictly preserved over time. This fundamental conflict between the macro-world of gravity and the micro-world of quantum mechanics is known as the black hole information paradox, and it remains one of the greatest unresolved conflicts in modern theoretical physics. The mystery deepened significantly when Stephen Hawking discovered that black holes are not completely static traps, but actually emit a faint trickle of quantum energy over immense timescales. This process causes the black hole to slowly lose its mass and eventually evaporate out of existence entirely, leaving behind nothing but a sea of random thermal radiation. If a black hole can completely vanish, the critical question arises: what happens to all the detailed information about the objects that originally fell into it? If the information is completely wiped out when the black hole evaporates, then the core laws of quantum mechanics are broken. If the information somehow escapes during the evaporation process, it would require a radical rewriting of Einstein's general relativity, suggesting that information can somehow leak across an apparently impermeable event horizon. For decades, the greatest minds in physics have wrestled with this dilemma, proposing radical solutions such as the idea that information is holographically imprinted onto the outer boundary of the event horizon, or that escaping particles are somehow scrambled like an unbreakable code. Yet no single framework has managed to resolve the contradiction in an airtight manner, leaving the fate of fallen matter locked inside an intellectual stalemate that touches the very foundations of physical reality. This brings us to a related phenomenon that has captured the imagination of scientists for decades, yet has never been directly seen by human eyes: the faint quantum glow known as Hawking radiation. When Hawking applied the principles of quantum field theory to the highly curved space-time surrounding a black hole, his mathematics yielded the shocking prediction that these objects must slowly radiate energy into the cold void of space. This mechanism occurs because the vacuum of space is continuously producing pairs of virtual particles that instantly pop into existence and annihilate one another. If a pair of these phantom particles materializes directly on the edge of an event horizon, one particle can be pulled down into the gravitational abyss before it can recombine. leaving its partner stranded outside the boundary to fly off into space as a real particle of radiation. Because this escaping particle carries away a tiny fraction of the black hole's energy, the black hole itself must inevitably shrink over time. While this concept is widely accepted within the theoretical physics community, it has never been empirically verified or observed in the actual cosmos. Real-world black holes are incredibly distant, and they are typically surrounded by swirling disks of superheated gas, dust, and violent magnetic fields that generate immense amounts of bright X-ray and radio emissions. This chaotic cosmic noise completely overwhelms the incredibly faint, icy trickle of Hawking radiation, making it virtually impossible to detect with any contemporary telescope or scientific sensor. Experimental physicists have tried to circumvent this technological barrier by building scaled-down analogues of black holes in laboratory settings, using sound waves in flowing fluids, or light beams in specialized optical fibers to mimic the geometry of an event horizon. While these fascinating experiments have succeeded in producing acoustic and optical versions of horizon radiation, they only provide indirect theoretical hints rather than definitive proof of celestial behavior. Until we can isolate and observe this quantum glow from an actual black hole in the deep cosmos, the reality of Hawking radiation remains an unproven prediction, keeping one of modern science's most elegant concepts trapped in the realm of theory. Even more mysterious than the edges of a black hole is the unfathomable point that lies at its absolute center, the gravitational singularity. According to the mathematical equations of general relativity, when a massive star exhausts its nuclear fuel and succumbs to its own immense gravity, its remaining matter collapses inward completely unchecked. Because there is no known force in classical physics capable of halting this downward plunge, all of that stellar mass is predicted to compress down into an infinitely small point with infinite density and infinite space-time curvature. This theoretical point is what scientists call a singularity. It represents a literal tear in the smooth fabric of space and time, a place where our current mathematical models completely break down and cease to yield meaningful predictions. The existence of a singularity is a glaring warning sign that our understanding of the physical universe is deeply incomplete. Infinity does not naturally occur in the physical world. Whenever our scientific equations produce an answer of infinity, it typically signifies that we are attempting to apply a theory outside the boundaries of its validity. To accurately describe what truly happens at the heart of a black hole, we desperately need a unified theory of quantum gravity, a framework that can seamlessly merge the gravitational mechanics of massive structures with the quantum rules that govern subatomic particles. Some modern alternative frameworks, such as string theory and loop quantum gravity, suggest that a true singularity might not actually exist at all. Instead, they propose that matter at the center of a black hole might be compressed into an incredibly dense, ultra-microscopic ball of fundamental energy strings, or that space-time itself becomes grainy and prevents infinite collapse by acting like a highly compressed quantum spring. However, because the event horizon completely conceals the interior of a black hole from the outside world, we are blocked from ever gathering direct observational data from within. The true nature of a singularity remains completely shielded from our view, enduring as an unreachable frontier that defies human comprehension. While black holes present an inescapable abyss, the universe also features regions that are completely empty on a mind-boggling scale, known as cosmic voids. When we look at the large-scale structure of the universe, galaxies are not scattered randomly throughout space like dust. Instead, they are arranged in an intricate web-like network composed of long bright filaments and dense clusters wrapped around massive pockets of absolute nothingness. These immense dark spaces are the cosmic voids, and they stretch across tens of millions of light years, containing virtually no galaxies, stars, or ordinary matter of any kind. They are the grandest, loneliest deserts in the entire cosmos, yet their origin and behavior present a massive puzzle for modern cosmology. According to our current models of cosmic evolution, These voids began as random density fluctuations in the primordial soup, immediately following the Big Bang. Over billions of years, regions of space that possess slightly more matter use their superior gravitational pull to steadily draw more material toward themselves, causing galaxies and star clusters to form along dense boundaries. Meanwhile, the underdense regions were systematically emptied, losing their sparse matter to the surrounding gravitational heavyweights and expanding into the colossal vacuums we observe today. However, the sheer size and profound emptiness of certain supervoids, such as the famous Botas void, continue to challenge our standard timelines of galactic growth. Some astronomers wonder if these voids might be expanding much faster than expected due to the unchecked influence of dark energy acting within their empty volumes. Others speculate that they could contain hidden forms of dark matter or undiscovered physical fields that actively repel ordinary matter. By studying the pristine emptiness of these voids, scientists hope to catch a clearer glimpse of the fundamental forces that sculpt reality. But for the moment, these vast gulfs of nothingness remain a silent, dark riddle spanning across the architecture of the cosmos. As if these structural vacuums weren't mysterious enough, astronomers have also identified a strange, large-scale, directional movement among galaxies that defies all conventional explanations. A phenomenon colloquially known as dark flow, when scientists analyze the cosmic microwave background radiation to track how clusters of galaxies move through the expanding universe. They expect to see them drifting in a largely isotropic pattern, moving away from one another in a uniform fashion dictated by the expansion of space. However, detailed observations have revealed that hundreds of massive galactic clusters appear to be marching in a synchronized, highly directed path toward a specific, localized patch of the sky between the constellations of Centaurus and Hydra. They are traveling at immense velocities, moving along a common trajectory that cannot be explained by any visible mass or gravitational source within our observable horizon. This unexpected celestial migration implies that something incredibly massive is exerting a powerful gravitational pull on our local region of the universe, from a position located completely beyond our observational boundary. One compelling but controversial hypothesis states that during the chaotic period of cosmic inflation immediately following the Big Bang, a massive amount of matter was pushed far outside our observable bubble. This external matter, though completely invisible to our telescopes, could still be casting a massive gravitational shadow that drags our local galaxies toward it. Another radical possibility is that our universe is directly interacting with an entirely separate neighbor universe within a larger multiverse structure, causing a gravitational distortion along the boundary zone. Many astronomers remain highly skeptical of dark flow, arguing that the perceived movement might simply be a statistical anomaly or an error in how we calibrate our instruments over such vast distances. The debate continues to rage within the astrophysical community, leaving us to wonder if our entire observable universe is being pulled through the dark by an unseen cosmic titan lurking just past the edge of sight. While we struggle to understand these massive directional movements across galaxies, the universe also bombards our planet with incredibly powerful, isolated bursts of energy that vanish in the blink of an eye, known to science as fast radio bursts or FRBs. These phenomena manifest as intense, sudden flashes of radio emission that typically last for only a few milliseconds, yet release as much energy in that single fraction of a second as our sun emits over the course of several days. They originate from deep extragalactic space, traveling across billions of light years of cosmic void before striking our atmospheric sensors with incredible intensity. Since their initial discovery in 2007, FRBs have become one of the most intensely studied and deeply baffling anomalies in modern radio astronomy. What makes fast radio bursts so incredibly frustrating to decipher is their extreme unpredictability and diverse behavior. Some FRBs are strictly singular events, flashing once with immense power before disappearing forever into absolute silence. Others are classified as repeaters, erupting from the exact same point in space multiple times over weeks, months, or years, sometimes following a highly structured periodic rhythm. Astronomers have proposed a wide array of theoretical models to explain their origins, ranging from catastrophic cosmic collisions, such as the violent merger of two ultra-dense neutron stars, to highly energetic flare events erupting from magnetars, neutron stars possessing magnetic fields trillions of times stronger than Earth's. Some early speculations even playfully wondered if these powerful directed beams could be the technological signatures of advanced alien civilizations utilizing immense energy arrays to power deep space sails. While modern consensus has leaned heavily toward natural, highly magnetic stellar phenomena, no single explanation can cleanly account for all the varied characteristics observed across different bursts. Until we can develop sensors capable of capturing these fleeting signals at the exact moment they ignite, fast radio bursts will remain brief, enigmatic shouts echoing across the universal void from an unknown speaker. In stark contrast to the chaotic unpredictability of fast radio bursts, the cosmos also contains objects that broadcast energy with a level of precision that rivals the finest mechanisms ever built by human hands: pulsars. Discovered in 1967 by astronomer Jocelyn Bell Burnell, pulsars are highly magnetized, rapidly spinning neutron stars that represent the crushed remnants of massive stars that perished in violent supernova explosions. As these ultra-dense spheres rotate, they emit intense, highly focused beams of electromagnetic radiation from their magnetic poles. If a pulsar's magnetic axis happens to be aligned in such a way that its beams sweep across Earth's line of sight, our radio telescopes record a highly regular ticking pulse of energy, functioning exactly like a celestial lighthouse, swinging its light across a dark ocean. When these signals were first observed, their absolute regularity was so startling that scientists seriously designated the source as LGM1, a playful acronym standing for Little Green Men, because they genuinely wondered if they had intercepted an artificial transmission from an intelligent extraterrestrial civilization. While we now fully understand that pulsars are entirely natural astrophysical objects, the staggering precision of their rotational rhythm continues to puzzle and amaze researchers. Certain variations, known as millisecond pulses, rotate hundreds of times per second, spinning with a stability that allows them to keep time with an accuracy that matches or exceeds our most advanced terrestrial atomic clocks. This leaves physicists with a profound structural riddle. How can a macroscopic object that contains more mass than our entire sun, yet is crushed down to the physical size of a small earthly city, maintain such a perfectly stable, unyielding mechanical spin in the midst of extreme gravitational and magnetic chaos? Even a tiny structural shift or a minor interaction with surrounding interstellar dust should disrupt this delicate balance. Yet these cosmic timekeepers march on without missing a single beat. They stand as beautiful, spinning paradoxes that challenge our understanding of how matter behaves under the most extreme pressures imaginable. Moving from these extreme stellar clocks to the massive bright engines that power the centers of ancient galaxies, we find ourselves confronting the deep enigma of quasars. Short for quasi-stellar radio sources, quasars are the most luminous and energetic objects in the known universe, shining with an intensity that can easily outshine an entire galaxy containing hundreds of billions of individual stars. They are powered by supermassive black holes, nestled at the hearts of distant galaxies, which actively gorge themselves on unimaginable quantities of surrounding gas, dust, and stellar material. As this matter is pulled toward the black hole by gravity, it forms a massive, swirling accretion disk that becomes superheated by friction and gravitational compression, releasing torrents of energy across the electromagnetic spectrum. The primary mystery surrounding quasars is not their general mechanism, but rather their presence in the incredibly early stages of cosmic history. When we train our most powerful space telescopes on the most distant quasars, we are looking backward across billions of light years, observing the universe as it existed when it was less than 1 billion years old. The data reveals that these ancient quasars were already being powered by supermassive black holes containing billions of times the mass of our sun. This presents a massive chronological paradox for astrophysicists. According to standard models of stellar growth, it should take billions of years for a black hole to steadily accumulate that much mass. There simply should not have been enough time in the young universe for these massive engines to grow. Scientists are left scrambling for an explanation, proposing radical ideas such as the direct collapse of massive primordial gas clouds that bypassed star formation entirely, or the rapid, chaotic merging of multiple black hole seeds in the high-density environments of the early universe. Until we can unlock the exact growth pathways of these primeval titans, quasars will continue to shine as brilliant contradictions that disrupt our established timelines of cosmic creation. While quasars illuminate the distant universe with immense power, our own home galaxy contains a massive structural anomaly that was only discovered very recently: the colossal energy bubbles known as Fermi bubbles, extending for tens of thousands of light-years above and below the flat plane of the Milky Way. These massive, hourglass-shaped structures emit highly energetic gamma rays and X-rays. Despite their enormous physical scale, they were completely invisible to traditional optical telescopes and remained entirely hidden from human knowledge until the Fermi Gamma Ray Space Telescope mapped the sky in 2010. They stand as silent, ghostly monuments wrapped around the core of our galaxy, leaving scientists deeply divided over their true origin. The leading theory suggests that these massive bubbles are the residual exhaust plumes left behind by a violent, energetic event that erupted from Sagittarius A star, the supermassive black hole at the center of the Milky Way, millions of years ago. Although our central black hole is currently relatively quiet, it may have experienced a period of intense feeding, swallowing a massive cloud of gas or tearing apart a whole cluster of stars, which triggered a massive blast of energetic particles that shot outward into deep space. Alternatively, some researchers argue that the bubbles could have been inflated by a sudden, intense burst of starburst activity, a period when millions of massive stars formed and died in rapid succession near the galactic center, unleashing a collective wave of supernova explosions. The primary challenge is that these structures are incredibly faint and difficult to analyze from our position inside the galactic disk. We can easily map their grand geometry, but the precise composition of the gas within them, the magnetic fields that hold them in place, and the exact timeline of their creation remain entirely unresolved, reminding us that our own galactic backyard still holds massive surprises. As we scale down our gaze from these grand galactic structures to the unique planetary architectures within our immediate neighborhood, we encounter the stunning, beautiful mystery of Saturn's rings. For centuries, these dazzling bands of ice and rock have been celebrated as the most iconic feature of our solar system, appearing perfectly stable and permanent to early astronomers. However, modern planetary science has completely upended this assumption, revealing that the rings are not an ancient, permanent fixture, but are actually a dynamic, temporary feature that presents a deep chronological puzzle. When NASA's Cassini spacecraft executed its daring close-up maneuvers around Saturn, it gathered precise measurements regarding the total mass and cleanliness of the ring material. To the surprise of many scientists, the data indicated that the rings are remarkably clean, composed of nearly pure water ice with very little accumulation of dark interstellar dust. If the rings had existed for billions of years, since the initial formation of the solar system, they should have become heavily dirtied and darkened by the continuous rain of micrometeorite impacts over eons. This pristine appearance suggests that the rings are incredibly young, potentially materializing a mere few 100 million years ago, a brief blink of an eye in cosmic history. This realization leaves scientists searching for a mechanism. How did such an intricate, massive ring structure form so recently in an otherwise mature planetary system? Some theorize that an icy moon wandered too close to Saturn and was violently torn apart by the planet's immense tidal forces, while others suggest a massive comet or asteroid collided with an existing satellite, shattering it into millions of icy fragments that gradually spread out into a flat disk. Furthermore, we now know that the rings are actively draining into the planet via a phenomenon called ring rain, meaning they are destined to completely disappear within the next few 100 million years. We happen to be living during the brief cosmic window where Saturn wears this magnificent crown, leaving us to unlock the fleeting secret of its beautiful origin. The great mystery that complicates our understanding of the universe's ultimate beginning is the nature of time itself. When we contemplate the cosmic dawn, we inevitably ask what occurred before that first explosive surge of existence. However, if the genesis of the cosmos simultaneously marked the literal birth of time, then seeking an era before it may be an entirely meaningless concept, much like asking what lies north of the North Pole. Our contemporary scientific apparatus, including the veteran Hubble Space Telescope, the Planck satellite, and the highly advanced James Webb Space Telescope, have provided us with breathtaking snapshots of the infant cosmos in its earliest states. Yet, despite their incredible engineering, none of these extraordinary instruments can look directly into that absolute first fraction of a second when reality ignited. We possess definitive evidence that the universe had a definitive beginning, allowing us to calculate its age with high precision, graph its outward development across billions of years, and analyze the fading cosmic microwave background radiation left in its wake. But despite all this data, the primary spark that put the entire clockwork mechanism of creation into motion, the true first cause of existence, remains an elusive secret cloaked in total darkness. This brings us to another profound riddle that we interact with every single moment of our daily existence, yet cannot truly clarify: the unyielding forward movement of time. Every single second that ticks by, the immediate present smoothly slides away into the permanent repository of the past. We possess the unique mental capacity to look back and remember what happened yesterday, but we are entirely incapable of remembering what will happen tomorrow. We witness a shattered glass lying on the floor, knowing it will never spontaneously reassemble its fragments and leap back onto a table. We observe heat steadily dissipating from a hot cup of coffee into the surrounding cooler air of a room, but we never witness the reverse scenario where a cold drink drinks in surrounding ambient warmth to boil itself. Within our macroscopic human experience, time is strictly a one-way street, a concept that theoretical physicists call the arrow of time. What makes this everyday reality so deeply bizarre is the fact that the foundational equations of physics do not actually require this forward-only orientation. When you examine the universe at the smallest subatomic levels, particles can interact, collide, and bounce apart in ways that make perfect mathematical sense, whether time runs forward or backward. The core mathematical laws of nature are almost entirely symmetrical, containing nothing that demands time must only advance into the future. Our macroscopic world relies entirely on a directional restriction that its fundamental building blocks seem to ignore. To resolve this deep contradiction, scientists frequently connect the arrow of time to the principle of entropy, which represents the natural physical tendency for structural order to degrade into randomized disorder over time. The universe began its journey in an extraordinarily ordered low entropy condition, and it has been steadily winding down like a massive mechanical clock ever since. This brings us face to face with an even deeper cosmological question. Why did the universe begin in such a highly organized state in the first place? What forced the initial cosmos to start in such a unique low entropy condition that allowed time to possess a clear direction at all? Some theoretical physicists propose that the arrow of time might not be a fundamental law, but rather an emergent property arising from the complex ways quantum information spreads across large systems. Others suggest that the forward direction is tightly bound to the continuous physical expansion of space itself. None of these contemporary explanations are entirely complete or universally accepted. Time's direction is a structural matrix that we occupy every single fraction of our lives. Yet the fundamental reason why it flows forward and only forward remains one of the most haunting and deeply resilient mysteries in all of modern science. When we lift our eyes to look at the vast architecture of the cosmos, we find that the vast majority of it is composed of an exotic substance that completely eludes our sight. When astronomers first began measuring the rotational velocities of distant spiral galaxies, they stumbled upon an anomaly that completely contradicted the laws of classical mechanics. According to gravitational logic, stars located near the outer fringes of a spinning galaxy should move much slower than those clustered near the dense center, much like planets orbiting far from our Sun. Instead, observations revealed that these outer stars are rushing along at incredible speeds, moving far too fast to be held in place by the gravitational pull of the galaxy's visible matter. By all traditional rules of physics, the immense centrifugal force should cause these outer stars to be violently hurled away into the deep emptiness of intergalactic space. Yet they remain firmly bound within their galactic structures, as if gripped by a massive, unseen anchor. The conclusion became completely inescapable. There must be an enormous amount of hidden mass residing within and around these galaxies that we cannot see, a cloaked substance that scientists have named dark matter. This mysterious material does not emit, reflect, or absorb light of any kind, rendering it completely invisible to even our most advanced telescopes. We are certain of its existence because its immense gravitational presence forcefully sculpts the behavior of everything we can see, binding galaxies together, warping the paths of starlight as it travels across distant clusters, and carving deep channels in the invisible cosmic web. For more than half a century, experimental physicists have conducted relentless searches to identify the true nature of dark matter. One prominent school of thought suggests it is composed of an undiscovered class of subatomic particles known as WIMPs, or weakly interacting massive particles, which possess significant mass but rarely interact with ordinary matter. Other researchers point to axions, which are theoretical, ultra-lightweight particles that would drift through the universe like ghosts, passing through solid worlds without leaving a trace. There are even alternative hypotheses suggesting that dark matter might not be a particle at all, but rather a vast population of primordial black holes that formed during the chaotic density fluctuations immediately following the Big Bang. Despite immense intellectual and financial investments, the identity of this material remains entirely unknown. Terrestrial experiments are buried deep underground in specialized mines, completely shielded from cosmic radiation, waiting for a single passing dark matter particle to collide with a heavily monitored atom. Decades have passed, and these sensors continue to record nothing but silence. For now, this hidden mass, which is 5 times more abundant in the cosmos than all the regular matter that makes up stars, planets, and human bodies, endures as an uncracked cosmic riddle, while dark matter acts as an invisible gravitational glue trying to hold structures together. An entirely separate opposing force is actively working to rip the universe apart at an ever-increasing rate. In the late 1990s, teams of astronomers studying the light coming from incredibly distant Type 1a supernovae made a discovery that completely shocked the scientific world. They fully expected their data to show that the expansion of the universe was gradually slowing down over time, a logical consequence of the collective gravitational pull of all the matter in the cosmos pulling inward on itself. Instead, the data revealed the exact opposite. The expansion of space is not decelerating at all, it is actively accelerating. This means that some mysterious repulsive energy is deeply embedded within the vacuum of space itself, functioning as a sort of cosmic anti-gravity that continuously pushes galaxies away from one another at faster and faster speeds as time goes on. Scientists have given this elusive phenomenon the name dark energy, though this title is essentially a polite placeholder for our profound lack of understanding. Dark energy is not a minor actor on the cosmic stage. According to current cosmological measurements, it constitutes nearly 70% of the total mass energy budget of the entire universe. Despite its overwhelming dominance, we remain completely ignorant of its fundamental nature. One leading hypothesis suggests it is a cosmological constant, an unvarying intrinsic energy property of empty space that remains perfectly uniform everywhere. Another interpretation proposes it is a dynamic shifting energy field called quintessence, which can alter its behavior and strength across cosmic epochs. Some scientists even wonder if dark energy is an illusion, signaling that Albert Einstein's theory of general relativity requires a fundamental rewrite when applied to the grandest scales of space. The ultimate fate of everything in existence rests entirely in the hands of this invisible force, making its mystery deeply unsettling. If dark energy remains completely constant throughout the future, the universe will experience a slow, lonely death known as the Big Freeze, where galaxies will drift so far apart that the night sky of any remaining world will become completely dark, leaving stars to burn through their fuel until the cosmos is nothing but a cold, dead expanse of widely separated particles. If this dark energy grows stronger over time, it could eventually trigger a catastrophic scenario known as the Big Rip, where the repulsive force escalates until it violently tears apart galactic clusters, then individual galaxies, then stars, planets, and eventually the very atoms that hold matter together. We can calculate its cosmic influence with remarkable precision, but we cannot see or touch its true essence. Dark energy remains the ultimate unseen director, silently steering the final destination of our universe into the deep future. As we examine the physical framework of our universe, we run directly into a deeply perplexing puzzle, known as the fine-tuning problem. The fundamental laws of physics are governed by a specific set of universal constants, such as the strength of gravity, the intensity of the electromagnetic force, and the masses of elementary particles. When scientists analyze these numbers, they discover that the cosmos appears to be balanced with impossible precision on a knife's edge. If the gravitational constant were just a fraction stronger than it currently is, stars would burn through their nuclear fuel much too rapidly, collapsing into black holes before planetary systems could ever stabilize. If gravity were slightly weaker, matter would never have coalesced together tightly enough to ignite star formation, leaving the universe as an eternal, sterile cloud of hydrogen gas. If the electromagnetic force were altered by even a tiny percentage, atomic nuclei would be unable to hold onto electrons, preventing the formation of complex molecules and rendering the chemistry of life completely impossible. Even minor adjustments to the strong nuclear force would mean that elements like carbon and oxygen, which are vital for organic life, could never be forged inside the hearts of supernovae. There is no clear, logical reason why these fundamental constants possess the specific numerical values they do. They could have theoretically been assigned any value across a vast spectrum, yet they occupy the precise narrow windows required to permit a complex universe to exist. This profound realization has led to intense debate among astronomers and philosophers alike. Some argue that this perfect alignment is a massive, inexplicable coincidence, a lucky stroke of cosmic fortune that we happen to inhabit. Others suggest that this fine-tuning points directly to the existence of a multiverse, a vast, grand collection of countless individual universes, where every single bubble possesses a completely different set of physical laws and constants. In this scenario, the vast majority of these universes are completely sterile, lifeless voids where matter cannot form correctly. We simply find ourselves living in an exceedingly rare, hospitable universe because it is the only type of environment where conscious observers could ever evolve to ask questions about fine-tuning in the first place, a concept known as the anthropic principle. A separate school of thought proposes that there may be a deeper, more fundamental law of physics that we have not yet discovered, a master equation that mathematically forces these constants to take on these exact values. For now, we are entirely unable to verify any of these explanations. When we look around at the stars, the planets, and the astonishing fact that we exist to ponder our own creation, we are reminded that our universe feels improbably, uncannily suited for existence, and the underlying reason for this compliance remains one of modern science's greatest unresolved mysteries. This structural wonder naturally leads us to ask another fundamental question about the grand architecture of reality. Does the universe go on forever, or does it eventually hit a boundary and end somewhere? The portion of space that we can actively see and measure, known as the observable universe, is a colossal sphere stretching roughly 93 billion light-years from side to side. As grand as this sounds, it represents a hard boundary imposed not by space itself, but by the speed of light and the finite age of the cosmos. Because the universe has only existed for approximately 13.8 billion years, light from objects located beyond that 93 billion light-year horizon simply has not had enough time to travel across the expanding void to reach our telescopes. We are permanently sealed inside an observational bubble, completely unable to see what lies past its outer edge. One major theoretical possibility is that the universe is truly infinite, an unending expanse that stretches out forever in every single direction, without any physical boundary or wall. If this is the case, the implications are mind-boggling, as an infinite volume of space would contain an endless number of galaxies, an infinite count of stars, and perhaps an infinite number of planets identical to Earth, where duplicate versions of ourselves are living out parallel lives. Another equally fascinating possibility is that the universe is finite in size but entirely unbounded, possessing a curved geometry similar to the two-dimensional surface of a sphere. In a universe shaped this way, if you were to step into a spaceship and travel in a perfectly straight line for a long enough time, you would never hit a dead end. Instead, you would eventually loop all the way around and arrive right back at your exact starting point. To determine the true shape and extent of the cosmos, cosmologists analyze the subtle temperature variations within the cosmic microwave background radiation, searching for geometric distortions that would betray the curvature of space. So far, the collective data gathered by our most precise space probes indicates that the universe is remarkably, almost perfectly flat. While a flat geometry highly favors the idea of an infinite universe, it does not completely settle the matter, as space could still be flat but folded into a complex, multi-dimensional shape that loops back on itself in ways we cannot easily visualize. For the time being, we remain completely ignorant of whether the cosmos extends outward without an end, or if it eventually circles back on its own structure. The true scale and geometric shape of the grand universe remain deeply hidden, positioned just beyond the reach of human intelligence. This permanent barrier means that just past the horizon of what we can actively see, there may lie an endless expanse of unknown realities. When we train our telescopes on the deep cosmos, we are not just looking across space, we are also looking backward through time. The light arriving from the most distant visible galaxies has spent over 13 billion years journeying across the expanding universe to reach our senses, showing us these structures as they existed when the cosmos was in its infancy. But beyond these ancient visible outposts lies a massive region that will remain forever hidden from our sight, the unobservable universe. This cosmic horizon is not a physical barrier like a stone wall. It is a moving boundary dictated by the age of the universe and the cosmic speed limit of light. We are entirely certain that reality does not simply stop at this line. The universe undoubtedly continues out into the deep dark, but we are fundamentally blocked from ever gathering direct information about what exists out there. It is highly possible that the unobservable regions are much the same as our own, featuring a continuous tapestry of galaxies, stars, and planets stretching out across vast gulfs of space. However, it is also entirely possible that these unreachable domains are radically different, containing regions that are governed by entirely different environmental conditions or operating under variations of physical laws that we have never encountered. Some advanced models of cosmic inflation suggest that our entire observable patch of space is nothing more than a tiny, localized bubble nestled inside a far more expansive, multi-tiered reality. If this hypothesis is accurate, the vast majority of the physical universe lies permanently outside the boundaries of what humans can ever measure, leaving us forever confined within a small cosmic island. The magnificent sky we gaze at every night is merely a tiny fraction of what actually exists, while the remainder of the universe sits out in the deep, silent, and entirely unreachable dark, a permanent unknown. This concept has driven some of the boldest minds in modern science to propose that our universe may not be unique at all, but rather one of countless individual worlds floating within a grand multiverse. The multiverse hypothesis suggests that what we have always called the universe is actually just a single drop in an infinite, chaotic ocean of separate universes. Within this vast landscape, each individual universe could possess its own unique laws of physics, its own distinct historical timeline, and even a completely different number of spatial dimensions. This radical idea is not just a fantasy cooked up by science fiction writers. It emerges naturally from the mathematical frameworks of some of our most respected physical theories. For instance, the theory of permanent cosmic inflation suggests that space is continuously inflating at a mind-boggling rate, with localized regions occasionally slowing down and pinching off to form distinct bubble universes, each possessing its own local conditions. Similarly, string theory, which attempts to describe the fundamental building blocks of matter, predicts that there are at least 10 to the 500th power possible configurations for the laws of physics, suggesting a vast landscape of different realities. In this scenario, our specific universe is simply one random outcome among an infinity of possibilities, which neatly explains the fine-tuning problem. We find ourselves in a universe perfectly suited for life, simply because it is one of the rare versions where conditions allowed conscious observers to evolve and ask questions. However, the multiverse hypothesis faces a massive fundamental problem that divides the scientific community. If these other universes exist entirely outside our own cosmic bubble and beyond our observational horizon, we may never be able to gather a single piece of empirical evidence to prove their existence. No light beam, gravitational wave, or physical signal could ever cross the immense gulf that separates our universe from a neighbor. This absolute lack of communication makes the multiverse both incredibly fascinating and deeply controversial among physicists. It aggressively stretches the traditional definition of science itself, because an explanatory idea that can never be tested, verified, or falsified through direct experimentation risks being relegated to the realm of pure philosophical speculation. Despite this barrier, the possibility that reality is infinitely larger, grander, and more complex than our single universe remains one of the most intriguing and mind-expanding mysteries in all of modern physics. This forces us to re-examine the very nature of the stage we stand upon, suggesting that space and time themselves may be woven from deeper, more fundamental rules that we have not yet discovered. Albert Einstein's revolutionary theory of general relativity completely transformed our understanding of reality by demonstrating that space and time are not a fixed, rigid backdrop against which events unfold. Instead, they are fused into a flexible, dynamic four-dimensional fabric known as space-time. This fabric can actively bend, curve, twist, and stretch in response to the presence of mass and energy, gracefully dictating the orbital paths of giant planets and steering the journey of starlight across the cosmos. But this realization leaves us with a profound, unanswered question. What is this fabric actually made of at its deepest, most microscopic level? When we try to examine space-time at the ultra-microscopic Planck scale, the smooth geometric rules of Einstein's relativity run into a violent collision with the chaotic principles of quantum mechanics. Relativity views space and time as completely continuous and smooth, no matter how closely you zoom in. Quantum theory insists that everything in nature must ultimately be grainy, quantized into discrete packets, highly fluctuating, and ruled by absolute uncertainty. Reconciling these two wildly successful but fundamentally incompatible descriptions of reality has stood for a century as the ultimate challenge in modern theoretical physics. To bridge this massive conceptual chasm, contemporary physicists have proposed a variety of radical new frameworks. Some models suggest that space and time are not fundamental properties of reality at all. Instead, they might be emergent phenomena that materialize from a deeper layer of existence, much like how the smooth macro property of liquid water emerges from the collective behavior of trillions of individual microscopic water molecules. In this view, space-time might be woven from an intricate network of subatomic quantum information or complex patterns of quantum entanglement that give rise to the illusion of geometry and distance. If this picture is correct, what we perceive as space and time is merely a surface projection, while underneath lies a bizarre, non-spatial reality that we cannot see. Other theoretical physicists openly wonder if time itself is an illusion, a psychological construct created by our brains to process a universe that is fundamentally static and timeless. If these theories are proven true, our most basic hardwired intuitions about the nature of our lives would be completely wrong. Space and time feel like the permanent stage upon which the entire universe unfolds, yet the stage itself may be an elaborate cosmic mirage, and what it truly represents remains one of the deepest unanswered questions in science. This sense of quantum weirdness becomes even more acute when we look at the individual subatomic components that make up the material world, where a single particle can seemingly exist in two different places at the exact same time. According to the well-tested mathematical equations of quantum mechanics, subatomic particles like electrons or photons do not possess a definite fixed position in space until they are actively forced into an interaction by a measurement. Instead, prior to being observed, they exist in a state known as a superposition, a delicate, ghostly cloud of overlapping probabilities, where multiple different locations and outcomes are simultaneously real. An individual electron can be here and there at the exact same moment, passing through two widely separated slits in an experimental barrier simultaneously, and then actively interfering with itself on the other side, much like a physical wave rippling through water. It is only when a scientific instrument or a human eye looks at the experiment that this probability cloud instantly collapses, forcing the particle to choose a single, localized point in reality. This is not just a wild philosophical concept or a mathematical trick. Decades of meticulous laboratory experiments have demonstrated superposition actively at work, not only with tiny subatomic particles, but also with complex molecules composed of thousands of atoms. Yet, despite our ability to calculate and harness this quantum behavior to build revolutionary technologies like quantum computers, no scientist truly understands what this phenomenon means for the nature of objective reality. Does the particle physically, literally, occupy two distinct points in space simultaneously? Or is a superposition merely a mathematical reflection of our own incomplete knowledge about a system? To explain this deep riddle, physicists have split into competing schools of interpretation. The many worlds interpretation suggests that reality continuously splits into a multitude of parallel universes every time a quantum choice occurs. One universe where the particle lands on the left, and another identical universe where it lands on the right. The Copenhagen interpretation suggests that objective reality simply does not exist in a solid form at the quantum scale, remaining completely fuzzy and unformed until an act of measurement forces it into a solid state. Whatever the ultimate truth may be, the undeniable ability of a single particle to occupy two places at once stands as one of the strangest, most deeply unsettling mysteries of the modern scientific age. The deep complexity of the subatomic world shifts into an even more confounding reality when we observe how entangled particles echo each other across massive distances of light years, completely defying any classical explanation. When two subatomic particles enter into a state of quantum entanglement, their fundamental physical properties become intimately linked in a manner that completely disregards the physical distance separating them. If you execute a measurement on one of these entangled twins to determine its state, you instantly and simultaneously gain absolute knowledge of the exact state of the other twin, regardless of whether it is positioned merely a few inches away or resting on the opposite side of a distant galaxy. Albert Einstein found this phenomenon so deeply troubling that he famously dismissed it as spooky action at a distance because it appeared to directly violate the sacred cosmic speed limit he had established. According to his well-tested theories of relativity, no physical signal, piece of information, or material object is capable of traveling through the vacuum of space faster than the speed of light. Yet rigorous modern physics experiments have repeatedly and definitively confirmed that quantum entanglement is an undeniable reality of our universe. Photons of light, individual electrons, and even small collections of entire atoms have been successfully entangled in laboratories and subsequently separated by many kilometers. Throughout these extensive tests, absolutely no physical signal, hidden beam, or energetic wave has ever been detected passing between the separated entities. Yet the correlations between their behavioral outcomes remain flawlessly and instantly perfect. It is as though nature itself is secretly maintaining an invisible, underlying ledger that operates beneath the visible surface of space-time, constantly ensuring that these distant outcomes stay completely in sync with one another. When physicists ponder what this shocking reality actually means for our understanding of existence, it leads to profound debates that shake the very foundations of philosophy. Some theoretical physicists suggest that reality is fundamentally non-local, meaning that the concept of separation in space is ultimately an illusion, and that everything in the cosmos remains fundamentally connected at a deeper level. Others wonder if it indicates that space and time are emergent properties arising from a dense web of quantum information, rather than being the primary building blocks of the universe. The absolute truth behind how two distant particles can communicate across the void without passing a signal through space remains an uncracked mystery that continues to challenge our comprehension of the cosmos. When we turn our focus away from the cold vacuum of the outer cosmos and peer inward at the complex architecture of our own minds, we run into an equally baffling enigma that resides right inside our skulls, the mystery of human memory. Every single day, your brain effortlessly records a continuous stream of experiences, allowing you to vividly recall the sweet scent of a flower from your childhood, the intricate details of a book you read years ago, or the comforting sound of a loved one's voice. And yet, the exact biological mechanisms regarding how those precious memories are permanently stored within the brain's physical tissue and how they are reliably retrieved when you need them remains a deep scientific puzzle. Neuroscientists have discovered that human memories do not exist as static, localized files neatly arranged inside a biological filing cabinet. Instead, they are dynamic, fluid patterns of electrical and chemical activity that ripple across vast networks of millions of individual neurons, spread out across entirely different regions of the brain. A specialized seahorse-shaped structure, known as the hippocampus, plays a critical role in weaving these disparate sensory patterns together, acting as a master index or conductor for our experiences. But the precise manner in which the brain physically encodes a fleeting moment into a permanent structural format, and the process by which it later pulls that specific pattern back into conscious awareness, is not fully understood. This mystery becomes even more complex when we examine how memories change, fade, or spontaneously rewrite themselves over time, showing that our mental archives are constantly in flux. When we sleep, our brains are actively restructuring these neural connections, deciding which experiences to discard and which ones to cement into our long-term identity. Yet the physical nature of the memory trace itself, known as the engram, remains largely hidden from our view. We can observe the brain's electrical activity lighting up on modern imaging machines, but we cannot decipher the deep code that translates those cellular signals into the rich tapestry of human thought and recollection. Memory is the invisible thread that binds our past to our present, defining exactly who we are as individual people. Yet the fundamental nature of this mental machinery remains one of the most resilient frontiers in all of cognitive science. This intricate connection between our mental states and our physical biology manifests in another deeply bizarre phenomenon known as the placebo effect, where the mere power of human belief can actively heal physical disease. In medical trials around the globe, patients are frequently divided into groups, with one group receiving an actual chemically engineered medication and the other receiving a completely inert substance, like a simple sugar pill or a harmless saline injection. Time and time again, a significant percentage of the patients who receive the fake treatment experience genuine, measurable medical improvements. Their blood pressure drops, their pain diminishes, their immune system strengthens, and their physical symptoms actively recede, despite having ingested absolutely no active chemical ingredients. What makes the placebo effect so uniquely strange and deeply perplexing to modern medical science is the fact that it can still function effectively even when patients are explicitly told that they are taking a completely fake pill. Somehow, the elaborate psychological ritual of receiving treatment, the act of consulting a trusted doctor, the physical swallowing of a pill, the sterile environment of a clinic, and the underlying anticipation of recovery directly triggers hidden, self-healing chemical pathways within the human body. Yet, the biological reasons why some individuals respond incredibly strongly to placebos, while other patients show absolutely no reaction, remains entirely unknown. The placebo effect completely blurs the traditional line that science has drawn between the human mind and the physical body, demonstrating that raw belief can sometimes repair cellular damage in ways that we still do not fully comprehend. It reveals that the brain possesses an extraordinary untapped pharmacopoeia of its own, capable of altering physical reality based entirely on perception. Despite decades of intense clinical study, the exact neurological trigger that converts a hopeful thought into a physical healing response remains a profound mystery, leaving doctors to wonder how deeply our thoughts truly shape our physical existence. This biological mystery deepens significantly when we consider that every single night, humans voluntarily surrender their conscious awareness to enter a state of prolonged vulnerability that we still cannot explain, the necessity of sleep. Every evening, we lay our bodies down, close our eyes, drift away into the surreal landscapes of our dreams, and completely lose track of the surrounding world for hours at a time. But when you examine this universal behavior through the strict lens of evolutionary biology, sleep appears to be an incredibly dangerous and counterintuitive evolutionary trait. In the harsh wild, an animal that is completely unconscious and unresponsive for a third of the day is profoundly vulnerable to predators, unable to hunt for food, incapable of defending its territory, and unable to protect its offspring. Yet despite these extreme evolutionary disadvantages, practically every single animal species on Earth participates in sleep in some distinct form, which heavily implies that sleep is an absolute biological necessity for life. But what is it essential for? Some scientists believe sleep helps the brain store memories and learn. Others think it clears away waste, cleaning the brain of harmful buildup. Sleep may restore energy, regulate emotions, and strengthen the immune system. It may even help the brain rewire itself, keeping connections balanced. And yet, no single explanation fits all the evidence. Different animals sleep in very different ways. Dolphins sleep with only half their brain at a time. Some birds sleep while flying. Some creatures need very little sleep at all. What we know for sure is that without sleep, minds and bodies quickly break down. Why we spend a third of our lives doing it remains one of science's great mysteries. The exact chemical or neurological trigger that demands our brains shut down every single day remains a deeply hidden secret, making our nightly descent into darkness a profound daily encounter with the unknown. As we progress through life, navigating the cycles of waking and sleeping, our bodies undergo a continuous slow transformation that points to another deeply resilient biological riddle: the process of aging. Every single complex living organism on our planet is subject to the unyielding march of time. As the years steadily accumulate, our skin naturally develops wrinkles, our hair gradually turns grey, our physical muscles steadily weaken, and eventually the structural integrity of the body begins to fail. But despite the universality of this physical decline, contemporary biological science cannot fully explain why aging happens in the first place, or why it manifests in such radically different ways across different species. One major scientific explanation points directly to our genetic blueprints. Every single time a human cell undergoes division to replicate itself, the protective caps located at the very ends of our chromosomes, known as telomeres, grow slightly shorter. Eventually, after a predictable number of divisions, these telomeres become completely depleted, causing the cell to stop dividing entirely and enter a state of decay. Another prominent theory focuses on accumulated environmental damage, suggesting that highly reactive oxygen molecules and other cellular metabolic byproducts slowly corrode our cells over time, leaving microscopic scars that continuously build up. Other researchers view aging as an inescapable side effect of evolutionary trade-offs, where natural selection prioritizes heavy energy investments into reproduction during our youth. leaving the body vulnerable to genetic decay once our reproductive years have passed. Yet nature presents incredible exceptions to these rules. Certain species of turtles, deep-sea fish, and unique organisms like the hydra display almost no measurable signs of aging whatsoever, maintaining their cellular vitality across centuries. The existence of these biologically immortal creatures proves that physical decline is not an inevitable mathematical law of matter, but a variable program. Why our specific genetic code commands our bodies to steadily degrade after a certain point remains an unresolved mystery, leaving the fountain of youth deeply buried in the complex labyrinth of cellular biology. While aging slowly transforms our physical bodies, our emotional lives are governed by a powerful, invisible force that completely dominates human behavior, yet completely eludes scientific measurement: the phenomenon of love. From an evolutionary perspective, scientists frequently attempt to reduce love to a basic survival mechanism, describing it as a calculated cocktail of hormones and neurotransmitters like oxytocin, dopamine, and serotonin, designed to foster parental bonding and ensure species reproduction. Evolutionary theory suggests it developed to keep parents together long enough to raise vulnerable offspring, but these cold, reductionist chemical explanations completely fail to capture the full, transcendent experience of human affection. Why does love sometimes arrive suddenly, overwhelming us? Why does it last a lifetime in some cases and fade in others? Why do people risk everything for it, even against reason? Love is not only chemistry or instinct. It is memory, story, and a profound psychological architecture that shapes human history. We can map the brain activity of a person in love and observe the reward centers lighting up like fireworks, but science cannot explain why a specific person triggers that intense reaction, while another equally suitable individual leaves us completely indifferent. It is a force that drives art, architecture, war, and sacrifice, yet it remains completely unquantifiable in a laboratory setting, enduring as a beautiful and deeply resilient mystery of the human condition. When we turn our attention away from human emotions and look down at the literal ground beneath our feet, we discover that the Earth itself is prone to producing spectacular, terrifying anomalies that science cannot fully comprehend, such as the eerie phenomenon of earthquake lights. For centuries, historical records have documented strange, luminous displays appearing in the sky immediately before, during, or after major seismic activity. Witnesses have reported seeing ghostly blue glows, flickering sheets of lightning-like fire, or floating globes of radiant light hovering above the ground as the Earth violently shakes. For a long time, mainstream scientists dismissed these stories as mere optical illusions or products of mass panic. But modern video recordings have proven beyond a doubt that these earthquake lights are entirely real. Yet what causes them remains unknown. One theory suggests that stressing rocks during an earthquake releases electrical charges, sparking light in the air. Another idea is that tectonic forces ionize gases near the ground, making them glow. But not every earthquake produces lights, and the appearances vary wildly. In some cases, the lights arrive before the earthquake, leading to speculation that they could act as a warning system. But their rarity and unpredictability make them difficult to study. Earthquake lights are among the most eerie natural mysteries, flashes of otherworldly glow in the midst of chaos, reminders that Earth itself may hold secrets written in fire and stone. This geological mystery is closely mirrored by the immense, unpredictable power of volcanic activity, where some volcanoes erupt with terrifying force, and the triggers remain mysterious. Volcanoes are among the most destructive forces on Earth. Most eruptions are dramatic but manageable: lava flows, ash blooms, small explosions. But every so often, a volcano erupts with unimaginable fury, blasting enough material into the sky to alter climate and spread devastation across continents. What makes some eruptions so catastrophic? Scientists know pressure builds as magma rises and gases expand, but the exact triggers that cause a volcano to transition from a steady, predictable release of energy into a world-altering cataclysm remain deeply hidden inside the subterranean depths of our planet. We can deploy arrays of seismometers, monitor gas emissions, and map underground magma chambers with satellite data, yet the ultimate internal mechanism that initiates these rare super eruptions continues to elude our complete understanding, leaving us at the mercy of the planet's hidden internal engine. Deep within that planetary engine lies another massive, invisible force field that protects all life on Earth from deadly space radiation, yet it is currently undergoing a slow, erratic transformation that scientists cannot fully explain. The reversal of Earth's magnetic field. Our planet is wrapped in a protective magnetosphere generated by the churning liquid iron outer core thousands of miles beneath our feet. This magnetic field acts as a vital shield, deflecting the relentless stream of high-energy solar winds and cosmic rays that would otherwise strip away our atmosphere and sterilize the surface of the world. However, geological records written in ancient volcanic rocks reveal a shocking fact. Earth's magnetic poles are not permanent fixtures. Every few 100,000 years, the field completely collapses and flips, causing magnetic north to become south and south to become north. The last major reversal happened about 780,000 years ago. But why do they happen? Scientists believe turbulence in the liquid outer core, the engine of Earth's magnetic field, sometimes becomes unstable, causing the field to collapse and rebuild in the opposite direction. But the exact trigger is unclear. Sometimes the flips are quick, sometimes they take thousands of years, and sometimes the field only weakens without fully reversing. The mystery deepens when we consider the effects. During a reversal, the field weakens, exposing Earth to more radiation from space. Would that disrupt ecosystems? Did past reversals influence evolution? We don't know. All we know is that Earth's magnetic field is not permanent. One day, north will again become south, and the reason why remains hidden in the depths. This planetary instability extends directly to our climate history, as ice ages come and go, and we still do not fully comprehend the ultimate drivers behind these massive glacial cycles. For billions of years, Earth has fluctuated between periods of extreme warmth and eras where colossal sheets of ice miles thick advance to cover entire continents. While astronomers point to subtle variations in Earth's orbit and tilt, known as Milankovitch cycles, as a potential clockmaker for these events, these cosmic shifts are not powerful enough on their own to trigger such radical planetary transformations. There must be complex hidden feedback loops involving ocean currents, atmospheric carbon dioxide levels, and volcanic activity working in unison to plunge the planet into a deep freeze. Yet the precise combination of events that sets an ice age into motion and the sudden triggers that cause the ice to rapidly melt away remains an uncracked puzzle, reminding us that the long-term future of our global climate is governed by forces we are still trying to map. When we lift our eyes from the history of Earth and peer across the solar system at our celestial neighbours, we find that these cosmic riddles extend to nearby worlds, most notably our neighbour Mars, where an entire planet's water supply vanished into thin air. Today, Mars is a frozen, hyper-arid desert, a rust-coloured wasteland swept by global dust storms. Yet, when our robotic rovers and orbiters examine the Martian surface, they capture undeniable evidence of our ancient watery past. We see massive, winding river valleys, ancient lake beds, delta structures, and coastlines that indicate a vast ocean once covered the northern hemisphere of the red planet billions of years ago. Mars was once warm, wet, and potentially hospitable to life, but then it underwent a catastrophic global climate shift. Where did all that water go? Some may be trapped as ice beneath the surface, some may be trapped in minerals. Much of it may have escaped into space when Mars lost its protective magnetic field. But the full story is unclear. Mars is littered with evidence of its watery past, yet its present is a desert. Did the water disappear slowly or in sudden shifts? Could liquid water still flow underground today, hidden from our view? The exact historical timeline and mechanisms that strip Mars of its life-giving oceans remain a major focus of space exploration, leaving the true fate of Martian water a haunting mystery. This leads us back to the most fundamental question that underpins all of physical science, a riddle that bridges the gap between quantum mechanics, astronomy, and philosophy. Is the universe fundamentally ordered or truly random? When we observe the cosmos on a human scale, it appears to operate with comforting, clockwork predictability. The planets orbit the Sun according to precise mathematical trajectories. Gravity pulls objects downward with unvarying consistency, and the laws of thermodynamics dictate the flow of energy with absolute certainty. This deterministic view of reality suggests that if you knew the exact position and velocity of every single atom in existence, you could theoretically calculate the entire future of the cosmos with perfect accuracy. However, the advent of quantum physics completely shattered this comfortable worldview. At the subatomic scale, nature appears to be governed by absolute irreducible probability and randomness. We cannot predict exactly when a radioactive atom will decay, or precisely where an electron will appear. We can only calculate the mathematical odds of these events occurring. This deep division has split the scientific community for over a century. Albert Einstein famously rejected quantum randomness, declaring that God does not play dice with the universe, believing that there must be hidden variables we have not yet discovered. Conversely, physicists like Niels Bohr argued that randomness is an intrinsic, fundamental property of the very fabric of reality. If true randomness exists, then uncertainty is not just ignorance. It is part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at the heart of physics. This brings us back to the master mystery that loops through every single topic we have explored. Time itself is still one of science's greatest mysteries. We live in time. We feel it flow second by second, carrying us from past to future, yet science cannot fully explain what time is. Einstein showed that time is not absolute. It bends and stretches depending on speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way street? Why can we not step backward into yesterday just as easily as we step forward into tomorrow? The absolute nature of this temporal river continues to mock our grandest formulas, enduring as the ultimate framework of our existence that we can measure with perfect precision but cannot explain. The deep mystery of how our physical reality operates shifts focus away from the microscopic collisions of quantum information and redirects our attention outward to the massive framework of the cosmos itself, where we encounter a realization that challenges the very boundaries of human reason. The laws of physics seem tuned for life in ways we don't understand. When theoretical physicists look closely at the fundamental numbers that govern our universe, they discover that our entire cosmos appears balanced on the knife's edge. If the force of gravity across the cosmos was even slightly stronger than it currently is, stars would burn through their fuel at an extreme rate and collapse too quickly, never allowing planets the billions of years required to develop complex life forms. Conversely, if the gravitational constant were just a fraction weaker than its actual value, matter would never have gathered together effectively after the dawn of creation, meaning that galaxies might never form at all, leaving the universe as nothing more than a thin, cold, and dark expanse of scattered hydrogen gas. If the electromagnetic force, which governs the behavior of charged particles and dictates how molecules interact, were different by even a tiny fraction, atoms would not bind together to form stable chemical elements, erasing the possibility of water, organic chemistry, or complex structures. Even the tiniest changes in the constants of physics, such as the mass of an electron or the strength of the strong nuclear force that holds atomic nuclei together, could instantly erase the possibility of life altogether, changing our vibrant reality into a completely sterile waste. This profound cosmic puzzle is known across the scientific community as the fine-tuning problem, and it raises deep questions that bridge the gap between hard physics and philosophy. Why should the laws of nature have exactly the values they do? And why do those specific values happen to match the precise requirements needed for complex living organisms to emerge? There is no obvious mathematical or logical reason for gravity, electromagnetism, or the various nuclear forces to take the specific strengths they have within our equations. They could theoretically have been assigned any random values whatsoever during the birth of creation, and yet, if they were different by even a little, our universe would be completely lifeless, lacking the structural stability to produce a single grain of sand, let alone a conscious mind. Some scientists argue this is a pure coincidence, a massive stroke of luck that we happen to inhabit a universe with the perfect conditions for life. Others suggest that countless universes exist simultaneously within a sprawling multiverse, each possessing radically different laws of physics, different constants, and different properties, and we simply live in the rare one where life is possible, representing a cosmic lottery win of monumental proportions. Another intriguing idea is that there may be a deeper, hidden principle of physics, still undiscovered by our modern instruments, that ultimately forces the laws of nature to take these exact values, showing that our universe could not have been built any other way. For now, we cannot say with any degree of certainty which explanation is true. But when we look around at the vast fields of stars, the complex mechanics of planets, and the astonishing fact that we can even ask this question, we are reminded that the universe feels improbably, uncannily suited for life, and why that is so remains one of science's greatest mysteries. This deep sense of planetary isolation becomes even more pronounced when we consider the physical scale of our cosmic home, because no one knows if the universe goes on forever or ends somewhere. The observable universe that we can actively detect with our most advanced technologies is genuinely vast, measuring about 90 billion light-years across from one edge of our modern celestial maps to the other, but we cannot see beyond it because of a fundamental physical boundary. Light travels at a fixed, unyielding speed, and it has only had so much time to travel across the void since the moment of the Big Bang took place roughly 14 billion years ago. And so, there is a strict horizon we cannot look past, a boundary where the light from more distant regions simply has not had enough time to reach our telescopes on Earth. But what lies beyond that edge of visibility remains completely unknown to us. One major possibility is that the universe is infinite, stretching endlessly in all directions with no boundary, no ultimate wall, and no physical end at all. If this scenario is true, then space may contain an unending number of galaxies, an infinite sea of stars, and perhaps even other Earth-like worlds populated by alternative histories. Another equally fascinating possibility is that the universe is finite but unbounded, meaning it has a limited volume but no actual edge, much like the two-dimensional surface of a sphere has a measurable area but no starting or stopping point. In such a universe, if you could travel far enough in one straight direction across the cosmos, your spaceship might eventually return to your original starting point after looping around the entire fabric of reality. Scientists continuously search for answers to this structural question in the cosmic microwave background, which represents the faint cold afterglow of the Big Bang that still permeates every corner of space. By analyzing the tiny temperature fluctuations and geometrical patterns written into this ancient radiation, researchers attempt to calculate the overall curvature of space to reveal the universe's true shape. So far, the evidence gathered by our satellite missions suggests that the universe is very nearly flat with an incredibly low degree of curvature, but this measurement does not fully settle the question of whether it is infinite or merely a small section of a larger structure. For now, we don't know if the cosmos stretches without end through the dark, or if it gently loops back on itself in a way that escapes our modern comprehension. The true size and shape of the universe remain hidden just beyond our reach, locked away behind the speed of light, leaving us to wonder about the nature of our cosmic architecture. Beyond the horizon of what we can see, there may be endless unknowns that we will never be able to verify. Because when we look into space, we are also looking into the past. Because light takes time to cross the massive gulfs of the cosmos. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years, showing us those structures as they existed when the universe was in its earliest infancy. But beyond that ancient light lies a region of reality that is forever hidden from human view, a space known to cosmologists as the unobservable universe. This cosmic horizon is not like a physical wall or a solid barrier in space. It is simply a temporary limit set by the age of the universe and the absolute speed of light. Beyond it, physical reality undoubtedly continues to exist, but we can never know exactly what is there, because no signal can cross the gap to inform us. Perhaps it is much the same as our own local neighborhood, with majestic galaxies, burning stars, and rocky planets stretching far beyond our sight into the eternal dark. Or perhaps it is radically different, with entirely different regions governed by completely unfamiliar conditions, or even different physical laws that would look totally alien to us. Some advanced theories of cosmic inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our entire observable patch of space is just one small bubble in a much larger, chaotic reality. If true, the vast majority of the universe lies forever beyond what we can measure, leaving us bound within a tiny cosmic island where the sky we see is only the smallest fraction of what may exist, while the rest of the universe sits out there, silent and unreachable, a permanent unknown. This concept of hidden realities expands dramatically when we look at the structural theories of modern physics, where some scientists believe there are other universes entirely, but we cannot prove it. The idea of the multiverse is one of the boldest and most controversial concepts in modern science, suggesting that our universe may not be unique, but merely one of countless others floating through a grander arena of existence. Within this theoretical framework, each individual universe could have totally different laws of physics, different historical timelines, different forms of matter, and even different numbers of dimensions that defy our human senses. This concept arises naturally in several of our most successful mathematical models of the cosmos. For instance, the theory of cosmic inflation suggests that space is constantly expanding and creating new bubble universes, each budding off with its own unique environmental conditions. Meanwhile, string theory, which attempts to unite all fundamental forces into a single framework, predicts a vast landscape of possible realities containing an unimaginable number of distinct vacuum states. In such scenarios, our specific universe is simply one random outcome among many, which could provide an elegant explanation for the fine-tuning problem. We live in a universe suited for life simply because only in such rare universes can conscious observers exist to ask these questions. But there is a major problem with this hypothesis. If these other universes exist completely beyond our cosmic horizon, we may never be able to observe them or gather any direct evidence of their existence. No light, no gravitational wave, and no physical signal could ever cross the boundary between separate realities, which makes the multiverse both fascinating and controversial to philosophers of science. It stretches the very definition of science because an idea we cannot test may never be more than mere mathematical speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. This structural uncertainty suggests that space and time themselves may be woven from deeper rules we haven't discovered yet. Einstein's general relativity shows us that space and time are not fixed backdrops or static stages, but flexible dynamic entities that actively interact with the matter inside them. They bend, curve, and stretch under the influence of mass, shaping the paths of planets and dictating the flow of starlight across the cosmos. But what, at the deepest level, is this fabric made of? When we try to examine the universe at the smallest possible scales, relativity and quantum mechanics clash in a violent mathematical contradiction. Space and time seem smooth, continuous, and highly predictable in relativity, but quantum theory suggests that everything at the subatomic scale should be grainy, fluctuating, and deeply uncertain. Reconciling these two views is one of the greatest challenges in modern science, leading to the search for a quantum theory of gravity. Some ideas suggest that space and time are not fundamental properties of reality at all, but rather emergent phenomena that arise from something deeper, perhaps a dense network of quantum information, or complex entanglement patterns that give rise to the illusion of geometry. In this picture, what we call space-time is like the smooth surface of a macroscopic object, and underneath lies a more basic informational reality we cannot yet see. Others wonder if time itself is even real, or if it is an illusion created by deeper, timeless quantum processes. If so, our most basic intuition about reality would be wrong, meaning space and time are not the stage on which the universe unfolds, but properties that emerge from a source that remains one of the most profound unanswered questions in science. This deep quantum strangeness manifests clearly in laboratory experiments, where a single particle can be in two places at once, and we don't know how. Quantum mechanics tells us that subatomic particles don't have definite positions or fixed properties until we actively measure them with an instrument. Instead, before an observation occurs, they exist in a superposition, a kind of mathematical probability cloud, where many different outcomes are possible at the exact same time. An electron can be here and there simultaneously, passing through both slits of an experiment at once, interfering with itself like a fluid wave. Only when we look does the particle choose a single place to appear. This is not just abstract theory. Experiments have shown superposition at work with molecules thousands of times larger than an electron. Physicists can create delicate states where macroscale objects exist in overlapping possibilities, and yet no one truly understands what it means for physical reality. Does the particle physically exist in two places at once? Or is superposition just a reflection of our incomplete knowledge? Some interpretations suggest multiple realities split apart every time a choice is made, creating one world where the particle lands here and another where it lands there. Others suggest reality itself is fuzzy until it is measured. Whatever the case, the ability of a single particle to seemingly be in two places at once remains one of the strangest, most unsettling mysteries of modern science. This eerie behavior deepens when we look at the historical balance of our universe, because matter exists, but antimatter nearly vanished, and we don't know why. When the universe began, the Big Bang should have created equal amounts of matter and antimatter, which is its perfect mirror image with opposite electrical charges. But when matter and antimatter meet, they instantly annihilate each other into pure energy. If they had been perfectly balanced at the dawn of creation, everything should have disappeared in a flash of radiation, leaving no stars, no planets, and no people. And yet, here we are. Somehow, matter won the ultimate cosmic battle. Why did matter gain the upper hand? Experiments show that matter and antimatter behave almost identically, but with tiny asymmetries known as CP violation. These slight differences may have tilted the balance in the early universe, but they do not seem large enough to explain why an entire universe of matter survived while antimatter disappeared. Finding the missing mechanism that allowed matter to dominate is one of the most important open questions in physics, touching on the very foundations of reality. This structural mystery is mirrored by our predictions of how black holes behave, as Hawking radiation is predicted, but no one has ever seen it. In the 1970s, Stephen Hawking made a stunning prediction that black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales until they evaporate entirely. This radiation, now called Hawking radiation, is one of the most famous predictions in modern physics, yet we have never observed it. Real black holes are surrounded by hot gas, dust, and violent environments that easily overwhelm the faint trickle of quantum radiation. Detecting it directly may be impossible with current technology, but the idea has huge consequences because it ties together quantum theory, relativity, and thermodynamics, suggesting space-time is more dynamic than we realized. Whether Hawking radiation truly exists remains unproven, leaving the ultimate fate of black holes shrouded in mystery. When we bring our focus back to our own planet, nature continues to produce anomalies that defy basic explanation, such as the baffling phenomenon of ball lightning. Instead of a quick bolt, it appears as a glowing sphere of light, floating silently, drifting across fields, or even moving inside houses. Witnesses describe orbs the size of a grapefruit glowing orange, white, or blue, sometimes lasting several seconds before vanishing or exploding with a pop. For centuries, ball lightning was dismissed as myth, a trick of the eyes, but recent credible sightings and scientific recordings suggest it is real. The problem is, no one knows what it is. Some theories describe plasma trapped by electromagnetic fields, while others imagine vaporized silicon glowing after a strike. Some suggest chemical reactions sparked in the air, but no explanation fits every account. The mystery deepens because ball lightning has been seen indoors, even floating through closed windows without shattering them. It seems to ignore ordinary physics, behaving like both matter and light, drifting through history as one of nature's strangest and most beautiful mysteries. A ghostly fire in the sky that reminds us how much we still have to learn about our own world. The deep quantum strangeness that leaves our best laboratories in a state of perpetual bewilderment does not stop with a single object existing in multiple places at once. It stretches outward into an even more jarring phenomenon, where entangled particles echo each other across vast light years, completely defying any ordinary explanation. When two subatomic particles enter into a state of quantum entanglement, their fundamental physical properties become linked together in an intimate manner that utterly ignores the vast distance of intervening space. If you alter or measure the orientation of one particle here on Earth, you instantly determine the corresponding state of its entangled partner, even if that second particle has drifted to the far edge of the Milky Way galaxy or into a completely different cluster of stars. Albert Einstein found this behavior so deeply disruptive to his sense of physical reality that he famously dismissed it as spooky action at a distance, because it appeared to directly violate the ultimate cosmic speed limit he discovered, which states that no physical signal, information, or force can ever travel faster than the speed of light. Yet despite his deep philosophical resistance, decades of increasingly precise and rigorous laboratory experiments have confirmed that quantum entanglement is an absolute, undeniable reality of our universe. Photons of light, microscopic electrons, and even small collections containing thousands of complex atoms have been successfully entangled in modern labs, separated by many kilometers of fiber optic cables or open air, and tested with rigorous precision. Every single time, no matter how quickly the measurements are performed, no signal appears to pass between the separated pairs, yet their mathematical correlations remain entirely perfect. It is as though nature itself keeps a hidden, universal ledger that operates beneath the visible surface of space and time, ensuring that these cosmic outcomes always stay perfectly in sync, without needing a physical wave to cross the gap. What this means for the true structure of our universe remains a fierce debate among theoretical physicists, with some suggesting that our classical concept of locality is entirely an illusion, and that everything in reality is interconnected at a foundational level. This foundational uncertainty regarding how our local environment interacts with larger planetary structures leads us back to our own home world, where massive geological forces operate on scales that dwarf our daily human experience. Yet we discover that the inner mechanics of supereruptions remain profoundly hidden from our view. While an ordinary volcanic eruption can devastate a local valley or disrupt regional airline flights for a few weeks, a supervolcano possesses the terrifying capacity to completely alter the climate of the entire planet, plunging the global ecosystem into a prolonged volcanic winter by choking the upper atmosphere with millions of tons of ash and toxic sulfur dioxide. We know that these catastrophic events have occurred at various points throughout Earth's long geological history, leaving behind immense collapsed craters known as calderas, such as the massive subterranean magma chamber that sits quietly beneath Yellowstone National Park. Our modern scientists continuously monitor these sites with arrays of highly sensitive instruments, tracking the subtle tremors of micro-earthquakes, measuring the escape of volcanic gases from hydrothermal vents, and using seismic waves to build rough three-dimensional scans of the shifting magma chambers deep beneath the crust. Yet, despite all of this high-tech surveillance, we still cannot accurately predict when a supervolcano might transition from a state of quiet slumber into a phase of active, world-altering eruption. Nor do we fully comprehend the precise triggers that cause millions of cubic kilometers of solid rock to melt and violently burst through the surface. Volcanoes serve as a powerful, humbling reminder that the very planet we inhabit is dynamically alive, driven by immense internal heat engines that generate mysteries we have yet to truly master. This continuous geological movement raises a much larger historical question about the outer architecture of our world, because why plate tectonics originally began on Earth is a matter that is still heavily debated across the geosciences. The solid surface of our planet is not a single unbroken shell of rock. Rather, it is alive with constant slow-motion activity. Continents drift across the globe over millions of years. Massive mountain ranges are forced skyward by immense collisions, and entire ocean basins slowly open and close over vast eons of time, all driven by the relentless drifting and grinding of tectonic plates floating upon the semi-fluid mantle below. Without the continuous action of plate tectonics, the Earth would completely lose its varied landscapes, its dynamic mountain ranges, its recycling systems, and its volcanic activity. In fact, many astrobiologists believe that complex life itself may fundamentally depend on this restless subterranean churning, which acts as a global thermostat by recycling carbon dioxide and keeping our climate stable over billions of years. But when we look at our nearest planetary neighbours in the solar system, we are confronted by a strange contrast. Mars and Venus show absolutely no signs of active modern plate tectonics. Their outer crusts are stagnant, locked into rigid, unbroken shells that trap their internal heat beneath a single piece of planetary armour. Somehow, billions of years ago, the Earth's crust managed to fracture into the giant sliding pieces we see today. Yet we do not know what triggered this unique division. Did the early presence of liquid water act as an essential lubricant, weakening the deep crustal rocks and allowing them to slide past one another into the dark interior? Did our planet's internal heat reach a highly specific, delicate balance between structural strength and fluid flow that was missing elsewhere? Or was the fracturing of our surface triggered by an intense bombardment of ancient asteroids that cracked the early crust open like an eggshell? Computer models continue to offer highly competing answers, but none have successfully explained why Earth alone developed this feature, leaving the origin of our planet's engine an unsolved puzzle. This planetary uniqueness becomes even more mysterious when we look down at the very fluids that make life possible, because the true origin of Earth's water is still highly uncertain. Water is the defining characteristic of our planet from space, appearing as a vibrant blue blanket that covers more than 70% of our surface, filling our vast oceans, carving out our river valleys, and drifting through our atmosphere in the form of clouds. It is the absolute foundation for every biological process we know, yet how it arrived here in such immense quantities remains one of science's great historical mysteries. One prominent school of thought suggests that our water was delivered to us from the cold, outer regions of space by a relentless bombardment of icy asteroids and comets during the chaotic, violent, formative years of the early solar system. While astronomical observations confirm that many primitive space rocks do contain significant percentages of water ice, the chemical fingerprints of Earth's oceans, specifically the ratio of heavy hydrogen to normal hydrogen, do not consistently match the water found inside the comets we have analysed with space probes. This discrepancy has breathed new life into an alternative theory, which proposes that our water was actually present within the rocky building blocks of the planet from the very beginning, trapped deep inside the Earth's hot mantle as chemical components within rocks, and was slowly released to the surface as steam through ancient volcanic activity over hundreds of millions of years. Perhaps the reality is a complex mixture of both ideas, with some water born deep within our world and some brought down from the stars, but the exact balance between these sources is still fiercely debated. What remains undeniable is that Earth is an incredible cosmic exception. Neighbouring worlds like Venus and Mars are completely dry wastes, having lost their water to space or locked it away in frozen soils. Something unique allowed our oceans to gather and remain stable for billions of years, reminding us that every drop of water we take for granted carries an ancient riddle, stretching all the way back to the birth of our world. Our sense of local mystery deepens when we lift our eyes from the oceans and look toward our nearest celestial companion, because the far side of the moon looks strangely different from the side we see, and we don't know why. For thousands of years of human history, mankind could only view a single face of the moon, because our satellite is tidally locked to Earth, rotating on its axis at the exact same speed that it orbits our planet. It was not until the Soviet Luna 3 spacecraft looped around the moon in 1959 and sent back the very first grainy photographs of the hidden side that scientists received a profound shock. The familiar near side of the moon is dominated by vast, dark, smooth plains of ancient volcanic lava known as maria, which form the patterns we traditionally call the man in the moon. However, the far side turned out to be a completely different world, almost entirely devoid of these dark volcanic plains, presenting instead a pale, heavily cratered and rugged expanse of mountainous highlands. This extreme structural asymmetry between the two halves of the same small celestial body has puzzled planetary scientists for generations. Why did volcanic lava flow so freely across the face that looks toward Earth, while remaining completely trapped beneath the surface on the side that faces the outer cosmos? Some modern theories suggest that the early Earth was incredibly hot after its violent formation, radiating intense heat toward the near side of the young nearby moon, which kept that side's crust thin and susceptible to volcanic outbursts from deep impacts. Other researchers believe that a second, smaller companion moon may have once orbited our planet before slowly colliding with the far side of our moon, pancaking across the surface and depositing a thick extra layer of crustal material that blocked any subterranean lava from ever breaking through. Despite analysing rocks brought back by Apollo missions and modern lunar satellites, the true reason for this split personality remains one of the solar system's oldest architectural secrets. This pattern of structural asymmetry and unexplained cosmic phenomena expands dramatically when we leave the Earth-Moon system and look out into the broader solar system, where we discover that an unknown source is heating the outer atmosphere of the Sun to millions of degrees. The Sun is a massive thermonuclear furnace, generating energy deep within its core through the effusion of hydrogen into helium, and as a result, we would naturally expect that the temperature should steadily drop as you move outward from the hot center toward the cold void of space. This holds true for the visible surface of the Sun, known as the photosphere, which sits at a blisteringly hot but understandable temperature of about 5,500 degrees Celsius. But as you move even further outward into the Sun's ghostly upper atmosphere, a region known as the corona, the laws of basic thermodynamics seem to completely break down. Instead of getting colder, the temperature of the corona explodes upward, reaching millions of degrees Celsius, making it hundreds of times hotter than the actual surface directly beneath it. This bizarre inversion is like walking away from a roaring campfire and suddenly finding yourself freezing close to the logs, only to be instantly scorched by intense heat once you step 10 meters back into the woods. For over a century, astrophysicists have struggled to identify the hidden mechanism that pumps this immense amount of energy into the thin gas of the corona. Some researchers point to the Sun's incredibly complex and twisting magnetic fields, suggesting that giant magnetic waves travel up from the interior and snap like whips in the upper atmosphere, releasing energy through a process called magnetic reconnection. Others investigate the potential role of nanoflares, millions of tiny continuous explosions that occur across the solar surface every second, each contributing a small amount of heat to the collective atmosphere. While modern spacecraft like the Parker Solar Probe are currently flying closer to the Sun than any instrument in history to gather data, the mystery of what fuels this ultra-hot solar halo remains an active question. As we look further out into the frozen expanses of our stellar neighborhood, the presence of liquid fluids becomes an even bigger puzzle. because vast oceans hide beneath the ice of distant moons, and we don't know what lies inside them. For a long time, astronomers believed that our own planet was entirely unique in possessing liquid water, assuming that the outer solar system was simply too cold for anything other than solid ice to exist. However, data sent back by planetary probes has completely shattered this assumption, revealing that moons orbiting gas giants like Jupiter and Saturn hold secret reservoirs of liquid water that contain far more volume than all of Earth's oceans combined. These hidden seas are kept liquid not by the dim warmth of the distant sun, but by the immense gravitational pull of their parent planets, which continuously knead and squeeze the moon's interiors through tidal forces, generating massive amounts of internal friction and heat. The most famous of these icy worlds is Jupiter's moon Europa, whose smooth, cracked surface of solid water ice conceals a global ocean that may be up to 100 kilometers deep. What makes these hidden oceans so profoundly exciting to modern science is their incredible potential for supporting extraterrestrial life forms. On our own world, wherever we find liquid water, we almost always find life adapting to it, even in the darkest, most hostile environments imaginable. Deep on our ocean floors, far beyond the reach of any sunlight, hydrothermal vents thrive with complex communities of unique creatures that draw their energy entirely from chemical reactions. If similar volcanic vents exist at the rocky bottoms of these alien seas, an entire biosphere of independent life could be swimming through the dark beneath kilometers of ice, waiting for our future robotic submarines to finally drill through the frozen shell and look into the deep. This tantalizing possibility of an alien ecosystem becomes even more concrete when we look closely at Saturn's small moon Enceladus, which actively sprays water into space, and we don't know what stirs below. Enceladus looks completely unassuming at first glance, appearing through telescopes as a small, bright, and featureless sphere of pure ice. But when NASA's Cassini spacecraft flew past this tiny moon, it made a stunning discovery. Giant geysers were actively erupting from deep fractures near the South Pole, spraying spectacular plumes of water vapor and ice grains hundreds of kilometers out into the vacuum of space. The spacecraft was able to fly directly through these celestial plumes, using its onboard instruments to sample the chemical composition of the spray, and what it found electrified the scientific community. The plumes contain not just pure water, but simple salts, complex organic molecules, methane, and tiny grains of silica that could only be produced by active hydrothermal activity where hot water interacts with a rocky core at high pressure. On Earth, these exact chemical ingredients provide the perfect recipe for the emergence of life, serving as the foundational environment where primitive microbes are thought to have first evolved in our ancient oceans. The geysers of Enceladus mean that we do not even need to land and drill through the ice to look for signs of life. The moon is actively throwing samples of its deep, dark ocean directly out into space for us to catch. Yet, because Cassini was not equipped with tools designed to detect living cells or complex biological structures, we still cannot say if those organic chemicals are merely dead planetary ingredients or the waste products of active organisms living around warm vents deep below the ice. This deep uncertainty regarding whether life is a common feature of the universe or a rare accident highlights the fact that we don't know if we are alone in the cosmos, which remains one of our oldest philosophical dilemmas. When we look up at the night sky, we see billions of stars within our own galaxy, and modern astronomy has shown us that the vast majority of those stars are orbited by their own systems of planets. Statistically, there should be billions of habitable worlds out there, many of them billions of years older than our own planet, which would have allowed more than enough time for advanced civilizations to develop and explore the stars. This glaring contradiction between the high probability of extraterrestrial life and the complete lack of any visible evidence or contact is known as the Fermi paradox. If the universe is teeming with life, where is everyone? Scientists have proposed countless theories to solve this silence, ranging from the idea that intelligent life is incredibly rare due to the sheer difficulty of the transition from chemistry to biology, to the more sobering concept of a great filter, a fundamental barrier that all civilizations eventually hit, such as nuclear self-destruction, runaway climate change, or artificial intelligence disaster, which destroys them before they can master interstellar travel. Other ideas suggest that alien civilizations might be actively avoiding us, treating Earth as a protected nature reserve, or that their methods of communication are so advanced that our primitive radio telescopes simply cannot tune into their signals. Until we find a single definitive sign of life beyond our atmosphere, whether it is a fossilized microbe on Mars, a chemical signature in the air of a distant exoplanet, or an artificial signal from the deep cosmos, we remain balanced between two equally terrifying possibilities. Either we are completely alone in this endless dark, or we share it with others who have chosen to remain silent. This profound cosmic isolation makes us look back at the history of our own neighborhood, where we find that the mysterious Planet 9 might be hiding at the edge of our solar system, and we haven't found it yet. For over a century, astronomers believed they had mapped all the major inhabitants of our solar system, but in recent years, a series of strange orbital anomalies has suggested that a massive, undiscovered world may be lurking in the dark far beyond Neptune. When researchers analyze the orbits of distant icy bodies known as trans-Neptunian objects that loop through the outer Kuiper belt, they discover that these bodies do not travel randomly. Instead, their highly elongated orbits are all clustered together, tilted in the exact same direction as if they are being continually pulled by the gravity of a large, unseen master. Detailed mathematical models and supercomputer simulations indicate that this gravitational pulling could be perfectly explained by the presence of a giant planet, roughly 5 to 10 times the mass of the Earth, traveling along a highly elongated path that takes up to 20,000 years to make a single trip around the Sun. If this planet, colloquially named Planet 9, truly exists, it would completely rewrite our understanding of how our solar system formed and evolved. The problem is that finding it is an incredibly difficult challenge, because at such an immense distance from the Sun, the planet would reflect almost no starlight, making it completely invisible to standard optical telescopes. It would be moving at a snail's pace through a massive haystack of background stars, requiring astronomers to use highly specialized infrared surveys to detect its faint internal heat. Until someone manages to capture a direct image of this phantom world through a telescope lens, it remains a mathematical ghost, a reminder that there could be a giant planet hiding right in our own backyard that has completely escaped human sight for centuries. This ongoing search for hidden celestial bodies reminds us that our universe is constantly producing violent energy signatures that we do not understand, such as the baffling mystery of fast radio bursts. These cosmic phenomena are incredibly intense, brief flashes of radio light that erupt from random points across the night sky, lasting for only a fraction of a millisecond, but releasing more energy during that tiny moment than our sun emits over an entire several days. Because they are so fleeting, astronomers struggled for years to even prove they were real, often writing them off as temporary electronic interference from equipment on Earth. But with the deployment of modern wide-field radio telescope arrays, scientists have confirmed that fast radio bursts are genuine cosmic events originating from galaxies billions of light-years away across the universe. What could possibly generate that much raw electromagnetic energy in a single millisecond is a question that has produced dozens of competing theoretical models. Some bursts appear to repeat from the exact same location in space, suggesting they come from a stable, highly active object like a magnetar, a type of neutron star with a magnetic field so intensely powerful that it can tear atoms apart. Other bursts are strictly single events, hinting at catastrophic, one-off cosmic explosions, such as the violent collision of two black holes, the merger of dense neutron stars, or the sudden collapse of an unstable star into a singularity. Despite detecting hundreds of these bursts and tracing some back to their host galaxies, no single explanation fits all the data we gather, leaving these ultra-powerful flashes drifting through the dark as one of the universe's most enigmatic and erratic signals. This problem of high-energy cosmic phenomena is closely mirrored by the mystery of ultra-high-energy cosmic rays. which hit our planet from deep space with an intensity that should be physically impossible. Cosmic rays are not actually rays of light. They are subatomic particles, mostly single protons or atomic nuclei, that travel through the void of space at speeds incredibly close to the absolute speed of light. Every day, millions of low-energy cosmic rays stream from our sun and hit Earth's atmosphere safely. But occasionally, our instruments detect an ultra-high energy cosmic ray with an amount of kinetic energy that completely defies comprehension. In 1991, physicists detected a single subatomic particle, famously named the "Oh my God" particle, that possessed as much kinetic energy as a professional baseball traveling at 100 kilometers per hour, all packed into a single microscopic proton. According to the known laws of astrophysics, no ordinary star or standard supernova explosion should ever be capable of accelerating a particle to such an extreme velocity. Furthermore, these particles should lose their energy rapidly as they travel through space by colliding with the ancient photons of the cosmic microwave background, meaning that whatever powerful engine created them must be located relatively close to our own galactic neighborhood. Yet, when scientists trace the arrival paths of these hyper-fast particles back out into the sky, they find absolutely nothing at their points of origin. No nearby supermassive black holes, no active galactic nuclei, and no violent stellar remnants that could explain the source of this incredible acceleration. They crash into our atmosphere, creating massive showers of secondary particles that we can measure on the ground. But the cosmic accelerators that launch them across the universe remain completely invisible to modern physics. This continuous encounter with deep space anomalies highlights a fundamental truth about our scientific progress. Our two best theories of the universe describe completely different realities, creating a profound paradox that no one has been able to solve. On one hand, we have Albert Einstein's theory of general relativity, which brilliantly explains the universe on a macroscopic scale, describing gravity not as a traditional force, but as the smooth, continuous bending of space and time around massive objects like stars and planets. On the other hand, we have quantum mechanics, which describes the universe on a microscopic scale with absolute precision, viewing reality as a grainy, uncertain arena where fundamental forces are carried by the chaotic exchanges of individual particles. Both of these theories have been tested over and over again in laboratories and through astronomical observations, achieving a level of mathematical confirmation that is unmatched in human history. Yet when physicists attempt to combine the mathematical equations of general relativity with those of quantum mechanics to explain places where the large and the small meet, such as the infinitely dense center of a black hole or the first tiny instant of the Big Bang, the math completely breaks down, producing nonsensical results like infinite probabilities and broken space-time geometries. This deep contradiction indicates that our understanding of reality is fundamentally incomplete, and that our two greatest triumphs are merely partial views of a deeper, grander framework of nature that we have yet to discover. For nearly a century, the greatest minds in physics have searched for a single unifying framework, often called a theory of everything, with candidates like string theory and loop quantum gravity offering fascinating possibilities. But so far, no experiment has ever been able to confirm them, leaving our view of the universe deeply fractured between two irreconcilable worlds. The incredible realization that our fundamental physics is locked in an irreconcilable conflict forces us to look closer at the individual celestial bodies within our solar neighborhood, where we observe that Saturn's massive shrouded satellite, Titan, possesses vast liquid seas made entirely of methane, and something out there must be constantly replenishing them. Titan is a uniquely mesmerizing world because it stands as the only moon in the entire solar system enveloped by a dense, thick atmosphere, presenting a landscape that feels strangely familiar yet entirely alien to human eyes. Space probes like Cassini and the Huygens lander have revealed a dynamically active surface complete with rolling sand dunes, carved river valleys, and immense placid lakes. However, on this freezing world, where temperatures hover around minus 180 degrees Celsius, water cannot exist as a liquid. Instead, it is frozen as hard as granite rock, while liquid methane and ethane flow through the landscape, taking on the exact role that water plays on Earth. They evaporate into the thick orange sky, condense into dark clouds, and pour down across the frozen terrain as torrential hydrocarbon rainstorms that feed the alien oceans below. Here lies the deep scientific riddle that continues to baffle planetary geologists. Methane molecules present in Titan's upper atmosphere are constantly being broken apart and permanently destroyed by the steady onslaught of solar ultraviolet radiation. Given the age of our solar system, all of the moon's surface methane should have completely vanished billions of years ago, leaving the world dry and featureless. Yet the vast lakes remain wide and deep, proving that a massive hidden source deep within Titan's interior must be continuously venting fresh methane back into the atmosphere. Scientists hypothesize that cryovolcanoes, ice volcanoes that erupt an icy slush of water, ammonia, and dissolved gases instead of molten rock, might be actively pumping fresh methane out from a vast underground reservoir. Others suggest that complex chemical reactions deep within the moon's hot core are continually generating new gases that slowly seep through the frozen crust. Until we send advanced robotic explorers back to explore the shores of these hydrocarbon seas, the true identity of Titan's internal engine remains an unsolved mystery. This planetary instability and continuous renewal leads us to ponder the very nature of physical reality itself, because we still do not know if the universe is fundamentally governed by absolute rules or if it is completely random at its core. For centuries, classical physics operated under the reassuring assumption that the universe was a giant, predictable clockwork machine. If you knew the exact position and precise velocity of every single particle in existence, you could theoretically use the laws of motion to calculate the entire history of the past and predict every event in the future with total certainty. This comforting view of a deterministic universe was completely shattered by the arrival of quantum mechanics, which revealed that at the subatomic level, nature refuses to provide definitive answers. Instead, particles operate on probabilities, existing in blurry states of potential until they are actively observed. A realization that prompted Albert Einstein to famously express his deep philosophical disgust by stating that God does not play dice with the universe. Yet modern experiments consistently demonstrate that true quantum randomness appears to be an unyielding, fundamental feature of our physical reality. This leaves us facing a profound philosophical split that divides the scientific community to this day. Is the universe truly chaotic at its absolute foundation, generating outcomes that are genuinely unpredictable and random? Or is there a hidden, deeper layer of deterministic physics, what scientists call local hidden variables, that we simply lack the instruments to detect, meaning that the apparent randomness is just a reflection of our own human ignorance? If the universe is truly random, then reality is built on a foundation of pure chance. But if it is ordered, then everything that has ever happened or ever will happen is already locked into an inescapable chain of cosmic cause and effect, an enduring paradox that sits at the very heart of modern physics. This continuous struggle to understand the basic mechanics of reality brings us back to a concept we interact with every single second of our lives, because time itself remains one of science's absolute greatest and most haunting mysteries. We measure it with incredible precision using atomic clocks. We structure our societies around its steady passing, and we watch its effects write themselves across our own faces as we age. Yet no physicist can truly explain what time actually is. Albert Einstein revolutionized our understanding by showing that time is not a universal, unchanging backdrop. Rather, it is flexible, dynamic, and intimately woven together with the 3 dimensions of space to create a 4-dimensional fabric known as space-time. This means that time is relative, stretching, and bending depending on the speed at which you travel, and the strength of the gravitational fields you experience. A clock placed on top of a towering mountain will tick slightly faster than a clock resting at sea level, and a clock traveling aboard a hyperfast spacecraft will slow down significantly compared to one left stationary on Earth. But while Einstein's equations allow time to expand and contract smoothly, they fail to explain why our human experience of time is strictly limited to a one-way street. We can move freely forward, backward, left, and right through the dimensions of space, but we are completely powerless to move anywhere but forward through the dimension of time, watching the present continuously slip into the unalterable past. Why we possess a clear memory of yesterday but can never see tomorrow, and why the universe is locked into this rigid progression, remains a profound question that general relativity cannot answer, leaving time as a mystery that governs us completely while remaining totally out of our intellectual reach. This fundamental asymmetry in the flow of time matches another grand cosmic imbalance that occurred during the violent creation of the cosmos. Because matter exists in immense quantities throughout the night sky, but antimatter has nearly vanished from the universe, and we don't know why. According to the foundational laws of quantum physics and the standard model of particles, energy can transform into physical matter, but it must always do so in perfectly matched pairs. Every time a normal particle of matter is created, an identical particle of antimatter must be born alongside it, possessing the exact same mass but an entirely opposite electrical charge. Because of this perfect mathematical symmetry, the intense energy of the Big Bang should have produced absolutely equal amounts of matter and antimatter at the very beginning of time. This creates a terrifying problem, because whenever a particle of matter comes into direct physical contact with a particle of antimatter, they instantly destroy each other in a violent process called annihilation, converting their entire combined mass back into pure, raw electromagnetic radiation. If the early universe had been perfectly balanced as the laws of physics demand, all matter and antimatter would have completely cancelled each other out within the first fraction of a second, leaving the expanding cosmos completely empty, filled with nothing but a uniform, featureless glow of light. There would be no stars, no spinning galaxies, no rocky planets, and no human beings to look up at the night sky. Yet when we observe the vast cosmos today, we see a reality made entirely of normal matter, with antimatter only existing in tiny, fleeting amounts inside high-energy laboratories or near violent stellar events. Somehow, an incredibly tiny asymmetry occurred during the first moments of creation. Perhaps just one extra particle of normal matter survived for every billion pairs that annihilated, allowing a small remnant of material to endure and form the entire visible universe. What specific process broke the perfect symmetry of nature and allowed matter to win the cosmic war is a riddle that continues to elude our best theoretical physicists. This profound mystery surrounding why anything physical managed to survive the birth of the cosmos leads us back down to our own world to examine the history of life itself, because the true origin of the very first biological cells remains completely unknown. We can trace the incredible story of evolution backward through billions of years of geological time, mapping how complex organisms develop from simpler multicellular life, and how those early creatures evolved from single-celled microbes swimming in the ancient primordial oceans. But when we push our investigation all the way back to the very beginning, we hit an absolute intellectual wall. We do not understand how dead, inert chemicals originally made the miraculous self-sustaining leap into active biology. The early Earth was a chaotic wasteland of volcanic activity, toxic gases, and shallow, mineral-rich seas. Yet somehow, within this stormy environment, simple organic molecules like amino acids and nucleic acids managed to organize themselves into the very first self-replicating structures. For life to begin, three completely independent and incredibly complex cellular systems had to spontaneously emerge and combine together at the exact same time. A genetic code to store and pass on blueprint information, a metabolic engine to draw energy from the surrounding environment, and a protective lipid membrane to keep all the chemicals securely contained within a single boundary. Scientists have spent decades trying to replicate this spark of life inside advanced laboratories, mixing ancient chemical soups and shocking them with electricity, or heating them over simulated deep-sea volcanic vents. But while they have successfully generated simple building blocks, they have never managed to create a living, self-sustaining, evolving cell from scratch. The transition from chaotic chemistry to organized biology remains a profound gap in our scientific understanding, leaving us completely uncertain whether the birth of life was an inevitable, natural consequence of chemistry that happens across the universe, or a bizarre, one-off cosmic fluke that occurred only here on Earth. This deep biological uncertainty directly influences how we view our place among the stars. Because despite our massive technological advancements, we still don't know if we are the only living world in the vast cosmos, or if we share it with countless other civilizations. When we look out into the night sky with our most advanced space telescopes, we are confronted by a staggering sense of scale. Our own Milky Way galaxy contains hundreds of billions of stars, and the observable universe holds trillions of individual galaxies, each filled with their own immense stellar systems. Modern astronomical surveys have revealed that planets are incredibly common, with almost every star we see hosting its own family of worlds, meaning there are billions of planets out there sitting in the habitable zone, where temperatures are just right for liquid water to pool on the surface. Statistically, the universe should be absolutely teeming with extraterrestrial life, and since many of these alien worlds are billions of years older than Earth, advanced technological civilizations should have had more than enough time to expand across space, leaving visible signatures of their engineering or radio communications across the cosmos. This glaring contradiction between the mathematically high probability of alien life and the complete deafening silence of the night sky is famously known as the Fermi paradox. If life is so likely, where is everyone? Scientists have proposed countless theories to explain this cosmic isolation, with some suggesting that the emergence of intelligent life is so incredibly difficult that it has only happened once, while others propose the chilling concept of a great filter, a fundamental barrier that all technological civilizations eventually encounter, such as nuclear annihilation, ecological collapse, or out-of-control artificial intelligence, which destroys them before they can achieve interstellar travel. Until we find a single definitive sign of life beyond our own atmosphere, we remain suspended between two equally staggering possibilities. Either we are completely alone in this endless cosmic dark, or we are surrounded by a silent universe of civilizations that we lack the ability to hear. This haunting sense of cosmic isolation naturally turns our focus inward to the hidden architecture of our own minds, where we discover that the true nature of consciousness remains an absolute mystery that science cannot define. Every single thing we experience in our lives, the vibrant colors of a sunset, the complex emotions of joy and sorrow, the internal voice that speaks inside our thoughts, and the very awareness of being alive, is entirely constructed within the dark, moist confines of our skulls, where a complex network of 86 billion neurons constantly fires off tiny electrical signals and exchanges chemical messages. We can use advanced medical scanners to watch the human brain in real time, mapping exactly which regions light up when we speak, move, or feel an emotion, and we can pinpoint how specific physical damages to the brain tissue can completely alter a person's memories, personality, and behavior. Yet despite this incredibly detailed physical map, neuroscientists have absolutely no explanation for how these purely physical, material processes give rise to our subjective, immaterial experiences of reality. This profound intellectual gap is known in philosophy and cognitive science as the hard problem of consciousness. Why should the mechanical firing of neurons feel like anything at all to the person experiencing it? Why does a physical brain translate the wavelength of light into the beautiful, subjective experience of the color blue, rather than just processing the information like a dead, unfeeling computer? Some researchers believe that consciousness is an emergent property that naturally arises whenever a physical system reaches a specific, highly complex level of information processing, meaning that sufficiently advanced artificial intelligence might one day wake up and become self-aware. Others propose more radical ideas, such as panpsychism, which suggests that consciousness is a fundamental building block of the universe itself, present in tiny amounts within every single particle of matter. Until we can bridge this gap between the physical brain and the subjective mind, our own self-awareness remains the most intimate and elusive riddle in existence. This realization that our own internal awareness is built on a foundation we do not understand mirrors our deep external ignorance regarding the final fate of the entire cosmos, because we still do not know how the universe will eventually end. Just as astronomers have used modern telescopes to peer backward through time and piece together the narrative of the Big Bang, theoretical physicists have used the laws of thermodynamics and general relativity to project our cosmic timeline billions of years into the future, mapping out several highly competing and deeply apocalyptic scenarios. The ultimate destiny of everything in existence depends entirely on the true nature and behavior of dark energy, the mysterious invisible force that is currently causing the expansion of space to accelerate at an ever-increasing velocity. If dark energy remains constant and unchanging over vast eons of time, the universe will experience a slow, agonizing death known as a big freeze or heat death. Galaxies will drift further and further apart until they are completely isolated in the dark. Stars will eventually exhaust their nuclear fuel and burn out one by one, and even massive black holes will slowly evaporate away over trillions of years through Hawking radiation, leaving the cosmos as a cold, dark, and completely uniform expanse of dead particles where nothing ever happens again. However, if dark energy steadily grows stronger and more aggressive over time, it will eventually overpower all the other forces of nature, resulting in a catastrophic event called the Big Rip, where space expands so violently that it tears apart clusters of galaxies, shreds individual stars, rips apart planets, and eventually tears individual atoms themselves into pieces. Alternatively, if dark energy should ever weaken and reverse its behavior, gravity could regain control of the cosmos, pulling all matter back together in a violent, reverse Big Bang known as the Big Crunch, crushing everything back into an infinitely dense singularity. Until we can decipher the true nature of the dark forces shaping our universe, the final chapter of our cosmic story remains completely unwritten, a mystery waiting at the end of time. As we look out across these vast, intersecting fields of scientific inquiry, stretching from the ghostly behavior of entangled quantum particles to the massive hidden engines of supervolcanoes, from the missing history of Earth's oceans to the silent expanse of the unobservable universe, and from the deep mystery of our own consciousness to the ultimate fate of the cosmos, we are forced to confront a profoundly humbling truth about our human journey. We live in an era of unprecedented technological triumph, where our robotic probes actively sail past the frozen moons of gas giants. Our supercolliders smash subatomic particles together at nearly the speed of light, and our advanced telescopes peer back to the very dawn of creation. We have compiled massive libraries of data, mapped the human genome down to the individual base pair, and written down mathematical equations that describe the behavior of nature with breathtaking accuracy. Yet for every single door of understanding we manage to unlock, we find ourselves standing before an entire corridor of completely new and even more complex questions, reminding us that our grandest scientific achievements are merely tiny islands of light shining within a vast, boundless ocean of cosmic mystery. This endless realization should not fill us with a sense of defeat or intellectual despair. Rather, it should inspire a profound sense of wonder and enduring curiosity, because it proves that the universe we inhabit is far more complex, beautiful, and magnificent than our human minds can even begin to fully comprehend. Science is not a rigid book of unalterable, final truths, but a living, continuous story that is still actively being written, and it is the very existence of these deep, unsolved puzzles that drives us to keep exploring, keep questioning, and keep searching the dark for answers. As you let the immense weight of these grand cosmic and terrestrial mysteries drift quietly across your mind. Notice how gently and effortlessly they begin to pull you toward a state of deep, peaceful rest. Like the slow, steady rhythm of ocean waves washing against a dark, silent shore, the unanswered questions themselves become deeply soothing, washing away the frantic stresses of the daily world and replacing them with a quiet sense of wonder. These ancient riddles do not require answers from you tonight. They do not need to be solved or managed before you can close your eyes. Instead, they only need to be carried gently in your thoughts, like the faint, distant starlight traveling across a wide and endless night sky. So let your breathing fall into a slow, natural, and rhythmic pattern, feeling your chest rise and fall with each passing moment. Let your physical body grow heavy and relaxed against your bed, and allow your thoughts to soften, release their grip, and gently dissolve around the edges. Imagine yourself floating weightlessly through the beautiful, unmapped mysteries we have explored together, passing by them as if you are drifting past glowing constellations in the deep dark of space. There are questions stretching infinitely above us, questions hiding deeply below us, and a magnificent galaxy of wonder surrounding us in every single direction, leaving you resting peacefully at the very quiet center of it all, completely safe in the comforting knowledge that mystery is not something to be feared, but a beautiful reminder that we are part of a universe filled with endless wonder